Hello everyone. Am I audible?
Yes.
Yes. Yeah.
Yes, so we are SMLRA, Sumaya Machine Learning Research Association, and this is our website. And over here, you can find various sessions that we have done over the past years, and it is in initiatives. So you can check out like what we have done in the past, so that you'll get an idea like what kind of a session we try to conduct. And previously, we had done ML-101 in 2020. There was one hackathon. There was PyTorch 101 session. We also discussed the paper in 2020, and similarly in 2019 and 2018. We have also done made some blogs on Medium website, and uh, after this ML-101, it would be helpful for you guys to go through that those blogs, because we'll be going through linear regression today. So you can go through this blog and understand the various mathematical uh, derivations in linear regression more in depth. And SVMs also, there is two series of blogs for SVM which are well written. So once it is done today, we can you can go and brush yourself up with the concepts. And there is decision tree which you can explore. And we have and this is our team. Our faculty is Swati Mali ma'am and Vaibhav sir, and I am the lead mentor along with Mayank Chaudhary. My name is Rahil Parikh, and we have community mentors as Jatin, Riya, and Burhanuddin. Then we have AI promoters, Jenson and Shubham. So we'll be together uh, doing this session for today, and some of our past council members are below. So yeah, let's get started with our today's session. Can you see the slides? Can anybody confirm?
Yeah.
Yes.
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 Yes, yes. Okay. So today we'll be discussing what is artificial intelligence first, because we all have a basic idea of what it is. So the basic definition of it would be that a computer system which is developed enough to perform tasks which require human intelligence. So what do we categorize as human intelligence? We can take example as visual perception or speech recognition, decision making, and translation between multiple languages. So that could be considered as artificial intelligence. So if you think like what does ML mean in intelligence, artificial intelligence, then you can look at this diagram and conclude that ML is a subset of artificial intelligence, and deep learning is a smaller subset of ML. So ML machine learning algorithms are basically algorithms used trained over time and over data to give predictions, and deep learning models involve multiple neural networks, and it becomes a black box after a point. So you can look at this graph whenever you're confused between what is ML and what is DL. Uh, Basically, there are two types for categorizing a model: parametric and non-parametric. Today we'll be covering both of these types of models. So in parametric, there are fixed parameters as input. So a model over time would have only those fixed parameters. So the parameters won't change over time. Even if the model is trained, it will accept only those input parameters. And in non-parametric, there are multiple parameters and they may change. So for example, parametric model would include linear regression, logistic regression, while in non-parametric, we can include decision trees, KNN. These are KNN is a clustering algorithm, which we'll be covering today. Then there comes two a kind of classification that is supervised and unsupervised. So these are two different techniques of creating a model and training it so that it gives us the expected work. The system works expectedly. So in supervised learning, we know what would come out. Like the system gives the output, and we are training it against the output. Like we can give the output, and the system can be trained against the output. But in unsupervised, we don't know what the output would be, and the system self trains itself. We don't have to uh, intervene ourselves while training. So today we'll be seeing both types of the supervised and unsupervised. And we all must have heard about reinforcement learning, which is a deeper topic, like which is more difficult than supervised learning. In reinforcement learning, you must have heard about like there are games which are being played by the machine itself, and it learns over time how to play the game. So today we won't be covering into linear regression, this reinforcement learning, but we'll be covering types of supervised and unsupervised. So as we know that linear regression and logistic regression all come under supervised, and unsupervised may clustering can come. So let's discuss what we'll be doing today. So today we'll be starting with linear regression, and in linear regression we'll be explaining what is gradient descent. Then we'll be heading to logistic regression, and then we'll be saying naive Bayes, k-means clustering, and support vector machines. Hopefully you'll have a good time, and whenever you have doubts, you can communicate with us by putting it in the chat or raising your hand, and we'll get back to you as soon as possible. And you can also ask question when the speaker is done speaking, and he'll say that if you have any doubts, you can ask your questions. So yeah, let's get started. And one more thing, there is this GitHub link in which we have one ML-101 notebooks inside this repository. So while we start with each of these concepts, we'll be also showing you some applications and some sample code that will be going through and explaining. So you can also copy this. You can open this in Colab and copy this Python notebook, and you can code along with us. Okay, with that, let's get started. So our first presenter would be Jenson with linear regression.
Hello everyone. Am I audible?
Yes, yes.
Hi guys. My name is Jenson. I am the AI promoter of SMLRA. Today we'll be going through what is linear regression. So let's get started. Can you see my screen?
Yes, Jenson.
Okay.
Yeah.
All right. Cool. Let's begin. So linear regression. As Rahil has discussed, various algorithms in machine learning, they can be classified into various types like supervised or unsupervised. So supervised, as he explained, basically means that we know what is we have a particular set of inputs and outputs, say suppose X and Y. The machine is going to predict something out of from the X values which we give. We know what the y values are, so we know what the result is. We can compare the result with what the machine is predicting, so we can compare how good is our model. Whereas in unsupervised, we don't know what the exact result is. The machine is just giving us just telling us how good or how bad the result is. We don't have a particular data set, or we don't have a definite value of definite measure of what is the output. So linear regression is a supervised means to supervised algorithm. So, so what will be going through in linear regression? We'll see what is linear regression, why do we use it, We'll see a realistic example based on it. We'll look at gradient descent. We'll go through polynomial regression, which is similar to linear regression, multivariate regression also similar to this. Then where is linear regression used in real life? And we can also jump to coding. What is linear regression? So when you hear this word linear regression, what comes to your mind? So if you ask me, I would say linear means line, right? And regression means relation between data points, that is x and y variables. Okay, so linear regression, we are going to do something from the data points. Basically, this x comma y, these are the data points. So to understand more, let me take an hypothetical example. So here, I imagine I went out and I did a survey. All right, I asked a few novel writers what is their experience, how many years experience they have in writing novels, and how many novels have they written in all those years. This is a hypothetical data. Okay, so suppose I asked a novel writer and he said, I have 2 years of experience and I've written 6 novels. I asked another one, he said, I have 4 years of experience writing novels and I've written 12 novels, right? So based on this pattern, 1, 3, 2, 6, 3, 9, 4, 12, 5, 15. If I ask you, if I went and asked a novel writer, and if he said that he has, say, suppose 7 years of experience writing novels. So can you predict based on this pattern? Can you predict how many novels will he will have written?
21. Yes.
21. Okay. So how did you know that it is 21? You found the relation between y and x.
7 3s are 21.
Yes, 7 3s are 21. So basically you saw that your y variables is 3 times your x variable, y equal to 3x. So you said, okay, if this relation is being followed, then if I say x equal to, say, suppose 7, then y is 3x. 3 times 7 is 21. So you can predict that if the experience of somebody, you did not know their experience, you do not know their how many novels they have written, but you knew their experience based on the current, based on this pattern which you have, based on the data which you have predicted how many novels he will have written. So that's what we do in machine learning. So this is an example of linear regression. Why? Because the y variable is linearly dependent on x. Say y equal to mx plus a, or here in our case y equal to 3x. So that's why it is called linear regression, because the y variable, the result is linearly depending on x. If you take this example, see, suppose this is also another hypothetical example. I took a survey of various groups where they breed rabbits. So they told that initially we had 4 rabbits in our group, and after 1 year, you know that rabbits, they reproduce very fast. So after 1 year, they told me that they have a total of 8 rabbits now. Similarly, they have. I went to another group. They told me they have 6 rabbits initially, and the after 1 year, the total number of rabbits they have is 27. Similarly, 8, 64, 10, 125, 12, 216. Can you tell me what pattern do you notice between x and y? Can you write a relation between y is some function of x?
X
And
upon 2 is equal to y cube.
sorry.
X upon 2 is equal to y cube.
Okay. So the relation is y equal to x by 2 whole cube, correct? So this is 4, so 4 by 2 is 2. So you cube 2, you'll get 8. You can take your example 10. 10 by 2 is 5. You cube 5, you get 215. Sorry, 125. So similarly, so y equal to x by 2 whole cube. All right. So based on this relation, so based on this pattern which you have observed, you have gone and collected this data. If I say that if there is a group, they have 14 initial 14 rabbits, can you tell how many rabbits there will be after 1 year?
7 cube.
Yeah,
340.
7 cube, 343. So you found a relation between the variables, and based on the existing data which you have predicted that if you get a new case where you get a x equal to 14 or x equal to, say, anything, so you can simply do x by 2 and whole cube, and that will be the predicted value based on the relation which you have established here. Now this is you have the relation is y equal to x by 2 whole cube. So it is not linearly depending, it's depending on the cube. So y equal to x cube by 8. Okay, that you can also write in that manner. So that's why it is called a polynomial regression. Y is not linearly dependent on x, it is a polynomial of x. All right. Okay. So this is I have taken this as a hypothetical example. So obviously in real life you won't get such perfect values. You won't get y equal to 3x or y equal to x by 2 whole cube, or you won't get such perfect relation between your data. Data, it may look somewhat randomized. So how will you what to say? How will you find the relation when you have such when you have data that looks a bit random? So that's what the concept of linear regression. All right. So before doing that, I'll just plot these two curves, y equal to x by 2 whole cube and y equal to 3x. And as I've mentioned that say I gave you a group of 9 rabbits. So after we have done plotted the graph, so we have taken the individual data points, we have plotted the graph. So based on the graph, we can have any value of x, and through the graph we can have a value of y. I request everyone to please keep themselves on mute. All right, thank you. So here, if you see when x equal to 7, when you have 7 rabbits, you may have approximately 45 or 43 rabbits after the end of 1 year. So we did not have the value for x equal to 7, but based on the graph, we plotted the graph first. We got the relation, and through the graph, we are finding what would be the value of y. Similarly, in y equal to 3x, we have plotted the relation. So this is linear regression, this is polynomial regression. All right. So in this linear regression, y equal to 3x. So if I say suppose y equal to 2.5. So you can immediately tell me, okay, what will be the value? So x equal to 2.5. You can immediately tell me what would be y if the x is 2.5. Can anybody tell?
7.5.
Yeah, 7.5, because you know the relation y equal to 3x, so you can tell it's 7.5 based on your existing relation. So we are going to do this when we have real life examples also. So this is a survey. So we have collected the data of what is the height in centimeters of a child whose age is given in months. All right. So we have surveyed multiple children. We have found out their height and their age. All right. So we have basically plotted the data points, and we have to find a relation. Now, if you see here, this the points, they don't lie exactly on the same line, right? So in real life you won't have relations like or not all points will exactly follow the relations. There would be some randomization. Say this point is above, this point is slightly above, this point is below. So our job is to plot the line which best matches or best represents these data points. So that is what we are going to do in linear regression. So did you all understand basically what we are doing in linear regression? We have this data. All right, we have this data. Our job is to plot the line in linear regression, to plot the line which best represents or best fits the data. And after plotting this line, now if you say if the age is, say suppose age in months is, say, suppose 26, then according to the line which we have plotted, we can predict, okay, what will be the value of height. Did you all understand?
Yes.
Yeah.
All right, thank you. So here basically our data, when we plot it, it may look something like this, right? There is not a like you cannot find, don't lie, all of them don't lie in a straight line, but they have a general trend like this. So we are interested in the trend. So based on the data points, based on the graph, we are drawing the line. So in linear regression, our job is to plot this line. That is what we are doing in linear regression. And after plotting this line, as I've mentioned, when you have any x value, you'll get the y value. All right. So this is a random. We can write a Python code for this to plot random points and to draw the graph of it. And using linear regression, we can draw the line. So we are going to see how we do that. Now, I've told that we have our job is to find the best possible line which passes through the data, right? So we need to plot the line like this. But how does the machine know what is the best line? Okay, so the machine itself will figure out how to find the best line. For that, we have algorithms. So we are currently understanding how the algorithm works. All right. All we are giving the machine is data. We are just giving data as I've showed in the previous example. Say suppose 1,3, 2,6, 3,9. We are just giving the machine data. The machine is going to do all the work for you. It is going to plot the line, and if you give any random x value, it is going to predict the y values. So that is what the machine is doing. So to understand the algorithm, to plot the line. Now to plot the line, we know the line equation, y equal to mx plus c. So m and c are the parameters of the line. Basically, if you change m and c to any values, you can get any line in the entire 2D plane. So based on your data, you need to have a value of m and c such that this line is perfectly aligned. All right, with me here so far?
Yeah.
Yes.
Okay. So
Yes.
this m and c is also called as hyperparameters because we are adjusting this m and c, and based on this m and c, we are going to plot the line and we are going to get our linear regression line. So how do we get the values of m and c? So initially, we take random values of m and c, or we can basically take m and c equal to 0. So m equal to 0 and c equal to 0. So we get a straight line through x-axis. And then we can tweak the value of m and c accordingly. We can increment or decrement the value of m and c accordingly so that it matches our desired value. It matches basically the data which we have. So now how do you define how good the line is, how good the line represent the points? For example, if I just draw a line, say suppose like this, you can see it does not match the data, correct? It is going out. It matches here, but it does not match here. The line is not a perfect fit. So how do you define, how does the machine define or know that this line is bad? Or how does the machine know that this line is bad? So if when you know this line is bad, then only you can tweak the line so that it may become more and more like this line, correct? So you need to have a measurement, a way to define how like how good or bad the line is. So for that, we introduce a function called loss function. All right. So a loss function is basically a means. It is basically a means to define how good our line is. Now I'll explain what is a loss function and how like why it is telling how good the line is. Now if you see here in this example, if you consider this line, all right. So this line, if you see the values on the line, say suppose these values, say suppose at 6 this value is there, at 8 this value is there. So these values are predicted values. The line is telling me what values of y is there based on the x. This is the data points, this individual points which we have, the data points. If you notice, if you observe, you can see that the predicted values or the points on the line, they are further away from the predicted values, correct? Whereas as you see the original line, the line which is giving us the linear regression, it is very close. In fact, it is passing through most of the data points. So the distance between the data point and the points on the line is minimum. Here you see the distance is way it is greater. So that is how we define our loss function. The more distance the points on the line is from the actual data, the more bad that line is. So the best line would be that it would give you the least error, or it would pass through most of the data, all right, and it will give you the least amount of error, correct? So the distance here is minimum. This distance is minimum, whereas as you see, this distance is so big. So this bigger amount of error, this slide will give you lesser amount of error. All right. So the formula for that is we calculate all such errors for a particular line, and we add such errors. Now this line, it will for example this line only, it will check this what is this distance. It will check this distance. For every value, every data point, it will calculate the distance between the point and the line. Between the point and the line. All right. So this here is distance less, but here the distance is greater. So it will calculate the distance between the point and the line, and what it will do, the distance, it will square the distance. It will square the error. That is, here the value is our actual value. The actual value, that is the value from the data, is yi. I denotes for I1, I2, I3 individual data. All right. And our predicted value is yr dash. So here, this is our yi dash. So this say suppose y3 dash. This point is y3 dash. And this value here will be our y3. So if you do y3 minus y3 dash, you will get this distance, correct? You're subtracting the y values. All right. So now if the points are lying above the curve, you may get a positive value. You may get a negative value. And if it lies below the curve, you may get a negative value. So we don't want the errors to subtract. We want the errors, the positive value of error. So that's why we square it, right? The square, what we do, take the yi minus yi bar. That is the point, the y coordinate of the data point minus the predicted y value. All right. And we square it so that our error does not become negative. We are only interested in the positive values. We do this for all the data points. For each and every value, we take the error, not for one value. That's why we have a summation here. We do this for all the values and we take the average. So we divide it by n. Understood this loss function? What we are doing here, we are taking the y, the y value of the data. Based on the current m and c values, we have a random line here. We are predicting how good or how bad that line is. So for that, line will have a particular equation. So y equal to, suppose 3x plus 5, something like that. Say for example. Then for at some x value, your x value, it will give some y value. The y coordinate you already have from the data. You'll take the subtraction, you will square it. All right. You do this for all the data points, and then you divide it by total number of data points. So that will give you the error function. The loss function. So that will be a measure. So the higher the loss function, the more worse your line is. The lower your loss function, the more better your line is. All right. So our job here by now you may have you will understand that our job here is to find the minimum of this loss function. We need to minimize this loss function, right? We need to find the line that passes through most of the points. So we need
Hello,
to
Jenson.
Yeah.
Yeah, there are two hand raised in the chat. I think they have doubts.
All right. I'll take the doubts. Pragat Singh, you have any doubt?
Yeah, I wanted to ask, is this the only algorithm that can be formed for linear regression, or there are other algorithms out there?
This algorithm is called ordinary least squares. All right, this is the most popular algorithm for linear regression. Or linear regression is basically the another term for linear regression is ordinary least squares. For plotting the data, you have many algorithms for finding the relation also. But this is the linear regression. This is the method used for linear regression or ordinary least squares.
Okay, thank you.
The main reason, wait, let the link go, I'll tell.
Sorry? Can you repeat?
Yes, just wait a minute. So the main reason we square the difference is so that we eliminate all the negative values.
Oh, yes, correct.
So like, can we also use mod of those values? Like all the negative will be eliminated.
You can do that, but in this linear regression, we are using ordinary least squares. So by the term only least squares, you know what we are going to do. We are going to square the terms. You may have known of absolute error, relative error, all those terms in statistics, right?
Yes.
Yeah. So we square the errors and we take the average. We take the average of all the errors, correct? So that's what we are doing here also.
Okay. Thank you.
All right. All right. So So now you understood what is the loss function. We have any random line. We are predicting how good or bad that line is. So we are calculating the loss function for that particular line, and our job is to minimize this loss function, and the line which has the least which gives the least value of the loss function is our linear regression line, is the line which we need. All right. So now do you understand that till now our job is to now reduce this loss function. We need to find the minima of this loss function. All right. Now how do we find the minima of this loss function? You can see 1 by n summation I equal to 0 to n, basically all of the data points by I individual values of the data minus yi bar the predicted values whole square. So how do you find the minima of this function? So for that we introduce gradient descent. All right. To find the minima of the function, we use the concept of gradient descent. Now I'm going to explain to you what is the concept of gradient descent. So imagine you're on a hill, right? And you're on a hill and you need to go to the valley, or you need to reach the valley. So do you just find the valley and jump in the valley, or do you take small steps to reach the valley? What would you do?
The second option.
The second option, right? Instead of directly jumping in the valley, you take small steps so that you gradually reach your valley. So that is what we are doing also here in the gradient descent. So gradient descent is an iterative algorithm. Iterative means it is running multiple number of times. It is constantly updating the values of particular variables, say suppose m or c, so that it can find the minima. It can find the minima of the particular function. All right. Now I'll explain to you how this gradient descent works. All right. So say suppose this is our function. I've taken the most easiest function, y equal to f of x. Say any f of x, and say suppose it looks like this. All right. This is our minima. All right. Why do we take random values of m and c? I told earlier, so that we reach a random point, and from there we start improving and reach our best values. All right. So this y equal to mx plus c. Now you understood. Now our job is to find the best values of m and c, so that we get the linear regression line. So instead of taking two variables, now just consider this y equal to f of x, only single variable, y is a function of x. Say this is y equal to x square or anything, any simple curve like that. All right. So initially we take some, say now this is a function in x. So we say suppose they say x equal to 3 something. All right. Any value, any random value in general. All right. From here we need to improve. We need to reach our minimum value. Or say I have taken your x1, y equal to x1 comma f of x1, x comma y, right? Y is f of x, so x1 comma f of x1. So how do you reach this minimum value? You need to go behind, correct? Now you are here, your x value corresponds to here somewhere. Say suppose here is 3. You need to come down, you need to come to 0. So you need to subtract, correct? You need to go behind. If say suppose if you are here, say suppose you are at -2. Say suppose this point is -2, this x value here is -2. You need to go ahead. So you need to add value to this -2 so that you reach 0. So just giving it in general x1. So you need to go, if the x1 is ahead of the minima, you need to subtract the value of x1 so that you reach the minima. So now say this here you have randomly taken any value. So here you have taken x equal to 3. Maybe you'll take x equal to -3. You don't know where the point is lying, whether it is ahead of the minima or whether it is behind the minima. So to fix that issue, we don't know where the point lies, right? So if it is ahead of the minima, we need to subtract the x values, subtract from the x value. If it is behind the minima, we need to add the x value. So what do you do to solve this issue? We find the slope of the at that particular point. See, suppose this is x1, this point is x1. We find the slope of, or we say find the derivative of x1, or derivative of the function at x1, and that gives us this slope. Correct? This is, suppose this is theta. So tan theta here, theta is tan theta will be positive. The slope is positive. As you can see, this line, the slope is positive. So what you do, basically now this slope will give you the sign, the direction where you need to go. If you notice here, the slope is negative. Here the theta is negative, tan theta will be negative. All right. So the slope, or f dash x2, the derivative of function at this point will be negative. So this will give you the idea. This will give you tell you where you need to go. So it is negative here, so you need to go ahead. You need to add the x value. If it is positive here, the derivative is positive here, you need to subtract. Correct? So now what you do, you take this is, as I mentioned, gradient descent is an iterative algorithm. Every time you're going to update the values of x. Say y equal to f of x. You have taken a random value. Now what you're going to do, you're going to do this. Say the next value of x is equal to current value of x minus f dash derivative at the particular point. Now this f dash xc here, as I mentioned, it is positive. So minus f dash xc, you will reach towards the minima. You're subtracting, right? So you'll reach towards the minima. If it is here the derivative is negative. If you subtract negative times negative, positive, you're going towards the minima. All right, understood this part? Any? All right. So I hope you understood so far. So now where we need to go to reach the minima. Now we need to decide what step size we are going to take, how much we are going to subtract. So like if you take large values, say suppose, yeah, we have a term here, say suppose L. L is called the learning rate, or basically this L f dash c f dash xc will basically define how big your step size is. So if you're subtracting this much x1, so L f dash xc suppose this much. So your x1 is here. Your new value of x1 will be this here. You will reach here. Again, you will subtract. You will reach here. Again, you will subtract. You will reach here. All right. That's how you reach the minima. So this L is a learning rate. If the L is too big, what will happen if the L is too big? You will subtract a very big value from here. You will reach at this particular point. You will subtract a big value. You will reach at this particular point. You will never reach the minima. It will keep on bouncing here and there. What will happen? You will keep bouncing here and there. You will never reach your minima. If you have a very large amount of L, say suppose L equal to 100 or L equal to 1000, for example, what will happen? You will never reach your minima. You will just keep on bouncing. The x values here, it will come. The derivative is positive here. It will subtract. It will reach here. Here it will find the derivative is negative. Again it will come here. Again it will come here. It will keep on bouncing. It will never reach your minima. So you need to have appropriate value of learning rate L, so that you will gradually reach your minima. Also, another use of this derivative, another helpful reason why we use derivative is that if you notice here, just observe this line, it has a particular slope. If you come here, you notice the slope has decreased. If you reach this point, you draw the tangent, you notice the slope has decreased more. Gradually, the slope is decreasing. That means gradually your f dash xc is decreasing, which means your step size is also decreasing gradually. So that's another advantage. So first your step size will be big, then it will be smaller, then it will be smaller, will be smaller, 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 and eventually it will reach your minima. If it is too big, you will not reach your minima. You'll just run through the minima. All right. So this is the concept of gradient descent. So basically, at every iteration, we are doing xn equal to xc minus L learning rate times f dash xc. This is a constant. Don't need to worry about that. So this is for a particular function y equal to f of x. That is how you find the minima of a function. This is the concept of gradient descent. Any doubt so far? Kazim, do you have any doubt?
सर वो ग्राफ कैसे प्लॉट होगा ग्रेडियंट डिसेंट का? आई थिंक वो सारे वैल्यूज को कंप्यूट करेगा और फिर वैसे जो ग्रेडियंट डिसेंट यूज करेगा.
The gradient descent, you don't need to plot the graph. I'm just plotting the graph for your understanding. We just need to do this. Just need to do these steps multiple number of times. All right. So the more number of times you will do, you will reach your minima. This is an iterative, right? Iterative algorithm. You just need to run a for loop. You need to do this algorithm, do this xn minus xc, xn equal to xn minus L f dash xc, and you'll reach your minima. All right.
Also,
yes sir.
So one more doubt.
Yeah.
Yeah, does the gradient descent compare the double derivative too? Because it can get confused between the minima and the maximum. So rather than getting the minimum value, we could end up getting the maximum value. Because
you don't need to worry about that. We are not calculating the double derivative. Now, as I mentioned, we are finding the minima, correct? if you calculate the if you want to find the maxima, basically you'll do a plus here. I don't want to confuse you, so don't worry about that.
Okay.
You're going in the direction opposite to the value of the slope. So your slope is positive, so you're subtracting. The slope is negative, so you're adding. So you will reach the minima.
Yeah, I understood.
I'll just
taking the right.
all right. So one more term I'll introduce here, epoch. So this is the total number of times you are running the algorithm. So this you have to run xn equal to xc minus lf dash xc. So you need to do this multiple number of times. So the total number of times you run this gradient descent algorithm, this iteration, that is called epoch. And as I mentioned earlier, larger learning rate, you will keep on bouncing back here and there. You will not reach your minima. If you have if you have very less value, you will take very small steps, and it will take lot of iterations. It will take say like 1,000 or 10,000 iterations, for example, and it is just time consuming and processor intensive. So you don't want that. You want a perfect value of learning rate. So it takes appropriate steps. You're a decent big size step, you're a smaller step, gradually reach your minima. So you'll get the value of x min, your current value, that is xn will gradually reach x min, and there you got your minima. All right. So that is what I have. The function here we have used is this, correct? We need to find the derivative of this function, this loss function 1 by n summation yi minus yi bar whole square. So we take the derivative. Now, if you just substitute the yi bar, the predicted value, our line equation is what? Y equal to mx plus c, correct? This is the individual data value. This is our predicted value which the line is giving. What is the y value? Y equal to mx plus c. Just substitute that. And now we need to find the best value for m and c. We need to find the minima of this loss function, and we need to find the value of m and the value of c such that the loss function is the least, correct? So we do it individually. First we find the value of m so that the loss function is least. Then you find the value of c so that the loss function is least. We take the partial derivative. All right. We take the partial derivative with respect to m. The partial derivative is almost the same as derivative, just that we are differentiating with respect to one variable. So we are differentiating with respect to m. So doing gradient descent algorithm with taking the partial derivative with respect to m will give us the best value of m. If we do it with c, taking the partial derivative with c, it will give us the best value of c. All right. And you know the gradient descent algorithm, the steps, m equal to m minus L into dm. This is the next value of m, current value of m minus learning rate times derivative with respect to m. Now, if you notice here, our function here was, what was the function? 1 by n is constant, leave it, summation yi minus mxi plus c whole square, here whole square. So take derivative with respect to m, 2 will come here. Then what you'll get, take the coefficient of m, that is minus x1, correct, minus xi, and this square will go away. That's what you have done here. Derivative with respect to m, partial derivative. Similarly, derivative with respect to c. Here, what is it? All right, derivative with respect to c is also similar. You can calculate derivative with respect to c. And xi value, you know the xi value. Yi value, no. Yi bar, you know, because you have a particular line, y equal to mx plus c. You have a particular value of m and c. All right. So you can find yi bar also. So this you will get the derivative. You can gradually get the best values of m and c. Now, how many times you run the iteration, that will define how good or how accurate your m and c values is. All right. So this was gradient descent. Any doubts so far? We are running a little bit short on time, so I'll just explain what is polynomial regression. Now, we have assumed a linear model, that is we are plotting a line, correct? We are plotting a line through our data. So in this case here, if you see, we are plotting a line which best represents our data. Say suppose our data trend is like this. Now you see the line won't match, right? The line is it won't be sufficient to consider a line, or a linear regression won't be it won't be sufficient. So we need to take polynomial regression. For the polynomial regression is the same as linear regression, except you are assuming y is not a linear function in x, y say suppose quadratic function or cubic function in x. All right, do you understand that? So we are not assuming y is in polynomial regression. We are assuming y is any polynomial in x, and we are defining what the polynomial is, whether it's a cubic or whether it's a quadratic. Because similarly, you will have these values, right? B0, B1, B2 for x raised to 0, x raised to 1, x square, right? So you will have the constant values. As we have found the best MNC values here, best values of MNC using this gradient descent concept. Similarly, you will find the best values of B0, B1, B2. Same thing we are doing. All right, just our function is changing. You have to take the derivative with respect to B0, then B1, then B2, and so on. And after running the algorithm, we'll get the best values. We can plot the value. We can plot our function, and whenever we give any x value, we can get a predicted y value. Is that fine? It's the same thing as linear regression.
Okay, a doubt.
Yeah.
How does the computer know that we have to apply the linear regression algorithm or the polynomial regression algorithm?
You
How
have to
does
tell
it
the computer. So you have to assume a model. You have to assume a linear model, or you have to assume a quadratic model or a cubic model. You have to assume. You have to tell, okay, what is my function? Whether my function is y equal to mx plus c, or whether my function is y equal to m1. So what would it be? Mx plus m2 x square plus c, something like that. You have to assume. All right.
Okay.
Okay. So that was polynomial regression. We are assuming a Weiss polynomial of x. Same thing as linear regression, just we are assuming it's a polynomial. Individual values b0, b1, b2 we need to find correct to plot the value. We are going to run gradient descent algorithm on each of them. So we get the best values for each of them. A multivariate linear regression. What happens? We have assumed Weiss only dependent on a one variable x. Correct. Many times in real life, you won't have that. You have so many factors to consider. Say suppose, what to say, the amount of say suppose there's a crop. The amount of yield would depend on the amount of water you're using and the amount of fertilizer. Right. Just an example. So it's just not depending on one variable itself. It's depending on multiple variables. So for that we use multivariate linear regression. All right. So what is multivariate linear regression? In linear regression, we assumed only one variable decides the value of x. Here we assume multiple variables contribute to y. Right? Y is, say suppose f of x1, ax1 plus bx2 plus cx3 plus so on, plus a constant term. So y is depending on multiple variables. All right. Now this multiple variables x1, x2, x3, they are called features. All right. So features of y. Y is the result what we are interested in. We need to plot y so that we get the multivariate linear regression. All right. So the method here to calculate is the same thing. How is it same? Because you already have the data for x1, x2, x3. Say suppose I gave you an example of crop yield. So your y is your crop yield. Your dependent variables is the amount of water and the amount of fertilizer you're using. You have done a survey, you have the data. So if I use, say suppose so and so amount of water and so amount of fertilizer, say suppose 1 liter of water and say suppose a few grams of fertilizer, just give an example, it will give me this much yield. Then another data you'll have, say so much amount of water, so much amount of fertilizer, you will have this much yield. You'll have a list, you have a table, you have the values of x1 and x2. You have to find the trend and you have to predict. If I have particular, say suppose something out of the data, say suppose 5 liters of water and say suppose say suppose 600 grams of fertilizer. So how much yield will I get, or what values, how should I adjust these so that I get the best yield? All those questions it can be answered if you do multivariate linear regression. The thing is, here you have mxi plus c, correct? The same concept you are using gradient descent. You are calculating a derivative. You are doing this, running this iterative algorithm. You are going to run the algorithm for each variable. For a, you are going to run. For b, you are going to run. C, D, every variable you need to run so that you get the values of every variable. best values of every variable so that you can plot the graph or you can get the curve. So here you will just have mxi plus m2 x2i, correct? So here will be the amount of water and there the amount of fertilizer, right? So you have the values of x1i and x2i. You just need to substitute it. So you will get the derivative. You can run the gradient descent algorithm. You can find the best values of that particular constant. So if you say x1, if you compare x1, you can if you do with respect to a. So A को तुम लोग you can find the best value, B को you can find the best value, C similarly n times the amount of coefficients you have, the amount of the unknowns you have. You'll run the algorithm, you will get the multivariate linear regression. All right. So where do we use linear regression in real life? I already gave the example. So agricultural scientists, they use this linear regression to measure the effect of fertilizer and water. So say here the B0 say crop yield is equal to say B0 plus B1 amount of fertilizer plus B2 amount of water. So if you adjust the value of fertilizer and water, you will get different crop yields, correct? And you need to find the trend so that when you have particular, say suppose I want to find what is the best crop yield, then you can find out. So if I use so and so amount of fertilizer and so amount of water, I'll get the best crop yield. This B0 is there because if you don't use any fertilizer, if you don't use any fertilizer and if you don't use any water, you'll still get some crop yield. It will be very poor, but you'll still get it. To account that we have B0. Similarly, in business, say suppose you are spending on ads. So the amount of revenue you're getting, based on the amount of money you're spending on ads. So if you spend more money on ads, you get more revenue. Correct. That is the general trend you see. If you don't spend anything on ads, you'll still get some revenue. You won't have zero revenue. So that is this B0. So you are finding in this case you are finding the relation between revenue and ad spending. Correct. So you can find out, okay, how much amount of money should I spend? What is the optimal amount of money I should spend so that I'll get the maximum revenue? Similarly, in medical researchers, we are going to take an example quickly. We are short on time. So blood pressure is a function of dosage. The drug dosage. So a particular drug has some effects on the blood pressure. So how is the drug affecting your blood pressure? So for that we have a relation. So through linear regression we can find that relation and we can effectively give the best dosage. So that's it. The theoretical part. We are quickly going to jump to coding. Any doubts so far in multivariate linear regression or? All right. So we are quickly going to jump to coding. So this is available in the GitHub repository, so you can check from there. This notebook. So this is the we have plotted the line. This is the code to plot the line. We are using matplot library. We're just quickly going through the code. All right. So this is simple function plotting. Don't need to worry about that. This is also simple function plotting. We are given the values of x and y. We are plotting here. We are using matplot library. The PLT is matplot library. This is the code to create plot random values. This as you see from the graph, to plot random values on the graph. So this np.random.rand state, it will give you the values between 0 and 1. It will give you an array and the array contains values between 0 and 1. And if you multiply it with a suitable coefficient, you can just create a line on your own. So this here the line is looks like y equal to 20x minus 8, right? Plus some constant, random constant, plus some constant, right? So this is basically a code to plot the random values. Our job is to find the linear regression line, right? So we'll have this data. You don't need to worry about plotting the data. We'll have this data from surveys or from anywhere. We'll have this data. We need to find the linear regression line. So we have used sklearn library, and sklearn, we have imported linear regression. We have created an object of linear regression. All right. If you are don't worry too much about the code. Basically, we are plotting. We are the function, the module, the method is doing everything for us. The logic is there in the method in the library. We are just what to say? We are just plotting the line. We are taking the help of the library. All right. So plt.scatter is a scatter plot. Plt.plot xfit comma yfit. This is a line which we are getting. I explained the concepts to you. The module does the same thing, right? So you don't need to code explicitly. So that was linear regression, and this is the concept which I've explained to you. Here we are actually plotting. Actually, we are calculating the derivative. So we have assumed a linear model, right? Linear regression. So the y value is m slope times x plus c. We have calculated the derivative as I have shown earlier. The formula for derivative, even here it is there. We have implemented this formula in our code. Epoch is the total number of times you are running the algorithm, as I mentioned earlier. So 1000 times you are running the algorithm to get the best values of M and C. All right. So every time M and C separately we are updating. Separately we are updating M and C. So it will gradually reach the best values. Does anyone have any doubt? All right.
The value of learning rate L equals to 0.001.
Yes. We have basically defined the learning rate L equal to 0.001. So I'll show you what that happens. What effect, what change does that do? So this is the code is to plot the line, and I'll just explain from here. So we have initially taken that m equal to 0 and c equal to 0, correct? That is our initial value, m equal to 0, c equal to 0. We have assumed learning rate as 0.001, correct? So that is why it is at this rate. As you see, the function is the line is getting plotted at every iteration. These are 100 times. If you run the algorithm, you'll get a line like this. When you run when you're at zero time, your line is y equal to mx plus c, and 0 m and c and 0 zeros initial values. 100 times after you run, it will become little better. It will look like something like this. After running 200 times the algorithm, your line will look something like this. Similarly, 300 times. If you increase the learning rate, say suppose if you increase the learning rate, then the line will become better, faster. So with less number of iterations, it will give you more precise line. So you can just see from here. Okay, so basically at every 100 iteration, we are printing what the line looks like. So after doing 1000 iteration, our line, our MNC values are almost perfect. We are getting very good values of MNC. As you have, okay, there's some error in the code. All right. So our learning rate may be too big, maybe. Let me just adjust that. So when you finally get a good line, which will, as you have noticed earlier, our learning rate was 0.05, so it was slightly bigger. So that's why it made a great change. Correct. So you need to have the learning rate is a constant, but you need to have an intuition, or you can just try and check it out. Or there are various algorithms also to find the best values of learning rate. We will not go discuss that here. So so after 1000 iterations, yeah, you can see that the m value is this and the c value is this. So this is our how our line looks in the final. Right. This is the best value of m and c for 1000 iterations. And in this you can find an animation like how your line gets adjusted. Like every time you are updating the values of m and c, so every time your line gets updated. So this is how your line, it is actually, the things are actually happening, right? So you have a line, more and more times you run the algorithm, you get more and more better values. That was linear regression. This is multilinear regression. Okay, so multiple variables. All right. So we have a code here. We have taken the data. We have taken Diabetes, we have taken a data set of diabetes. So basically diabetes, we have to measure how diabetes is getting worse over time for multiple people, right? So disease progression. So we have used linear regression for disease progression. So the y value is quantified as response of interest. So we are basically measuring how worse the diabetes is. Diabetes is based on the response of interest, which might be a medical term. All right. So you know that diabetes, the stage 1 diabetes, stage 2 diabetes, pre-diabetes, right? So we are basically finding out the relation between we have went out and we have done a survey. We have got the data. We have created the model, that is we have created the linear regression line, and we have variables now. How many variables we have? We have 10 variables here. So this diabetes depends on 10 variables: age, sex, body mass index, average blood pressure, and 6 blood serum levels. So after successfully running this algorithm, if you have a set, say suppose you want to find how likely you are to get the diabetes, so you'll give your age, your sex, your body mass index, so all the x values, and based on the current relation, on this current relation, you're going to predict how likely you are to get diabetes, or what is your stage of diabetes, what is your likely stage of diabetes. All right. So we are using sklearn, and we are sklearn library. We have imported the diabetes, all right, into this diabetes variable. We have the data here. The data we have 442, the data of 442 patients. There are 10 variables: age, sex, body mass index, average blood pressure, and 6 blood serum levels: S1, S2, S3, still S6. These are our xi values, as I mentioned here now. These are xi values, right? And it is giving the measure of diabetes. So we are this is the description. We are printing the description. So this is basically giving the information of the data which we have. Then we are running the model. What we have done, we have the diabetes data. We have to split the data. Now we are splitting the data. 80-20 split means 80% of the data we have a data. So as I mentioned, this is supervised learning. So we know what is the output, right? So 80% of the data we are using to train the model. 20% of the data we are using to test the model, to test how good our model is. So 80% is for training, and 20% of the data which we have is for testing. So x train, x test, y train, y test, different variables. This function is splitting the data, and it is the individual values are assigned. All right. So our we have created an object of linear regression. Now model.fit x train, y train, it basically trains our model. Okay. So we have assumed a linear regression model. Somebody asked which where we have to assume. Yes, we have to assume linear regression model. We have trained the data using model.fit x train, y train. Now here the model gets trained. So these are methods, right? So the code, the actual part, it is being done. You don't need to worry about that. This running this code simply does everything for you. So when you do model.predict x test, now after finding the relation between your x train and a y train, when you predict your x test, what would the values look like? So this is how the values would look like. All right, the 20% of the data, and now you will compare it with your y test, correct? So that you can understand, okay, this is the error, or this much accurate my model is, or this good my model is. So we have also used one more library, stats model. So we have used that model, we have used that library to find the summary of the model. So basically we are don't worry about the details. We are basically printing the summary of the model, what we have done so far. So here the important thing you have to notice that we are using OLS, as I mentioned, ordinary least squares, the method, or linear regression is another name, ordinary least squares. R square is the measure of, this is the important thing here, R square is the measure of how we can how much we are able to predict the y variable. So the y result, we are able to predict 48.8%. Only 48.8% we are able to predict. The rest may be random or noise, like the rest may be error or noise, and the model is not able to predict that. All right. So assuming a linear model. So that's the code here. One more important thing here. For our model, the constant, this will be our, say this is y equal to m1x plus m2x2 plus m3x3. x1, x2, x3 are variables here. So age, sex, and BMI, and blood serum levels. So these are our x1, x1 to x10 values. This is the constant value, the y-intercept, the value of the term, say suppose m1x. So this is the value of m1, m2, m3, and so on. All right. So this, we are using this stats model library to basically print the summary of this. So we have successfully created the linear regression model to find the disease progression of diabetes. So like anyone of you has any doubts? Do you have any doubts? Who is this?
Yeah. I actually wanted to ask what percent of data should the model be able to predict correctly to be considered a good model?
So it depends. So now you will use your model for various purposes, like for the crop yield you may use, for the what is it, business models you use. For business models and all that, I would reckon that 50% and above, greater than 50% would be sufficient. When it comes to now, this is diabetes prediction, right? So I would reckon that about closer to 50% the percentage accuracy is sufficient. Basically, this 0.488 or 48.8% basically means you can justify the changes in your y, that is your disease progression, based on the 48%, 48.8% you can justify it based on the current trend. So it could be that the variables are not following the trend for some reason. So that would be the noise, that would be the error. So that you cannot justify, but the model can justify 48.8% of the changes that is happening in the y. Is that fine? All right. So if we are done here, I'd like to quickly hand over to Shubham to take the session on logistic regression. Thank you, everyone.
Just to interrupt you, Jenson, I'll add to your explanation regarding that doubt. In business problems, there is certain business metrics which we have in order to, tell कि ये मॉडल इतना चलेगा. So based on the criticality of the application, अभी जैसे diabetes prediction है और take something more serious, cancer prediction. So in those cases, there are other metrics, not just accuracy. In those cases, it is very critical कि अगर किसी को कैंसर है और तुमने उसको ना बोला, तो ये बहुत ज़्यादा हैजर्डस है एज कम्पेयर टू सेइंग कि तुम्हारा यू डोंट हैव कैंसर बट गलती से कैंसर बोल दिया. So based on case to case basis or business application, the accuracy और other metrics कितना होना चाहिए वो changes. तो जैसे कैंसर prediction है तो इसमें even a 99% accurate model is not good, considering कि हर 100 लोग में वो एक गलती करते हैं. So you would need something like 99.999 something or like that. But if you go for a less critical application, so you can expect the 90-95% predictions or even 75-85% predictions are reasonable enough. So whatever is the business use case, on the basis of that, your accuracy and all will depend. Now, if you're doing some college project or something, and when you will see your criticality of the application, then you will realize कि ठीक है अभी हम लोग अपने लिए कर रहे हैं तो 75-80 is good. But when you will scale it up to business level, it can be more than sufficient or it may be very less than sufficient. So we cannot give one answer कि इतने के ऊपर है तो model is good.
Okay.
So hello guys, am I audible?
Yes.
Okay, so I'm Shubham Varma. I'm AI promoter at SMLRA. So now I will be taking logistic regression. So now first of all, distinguish between what was linear regression and what is logistic regression. So as very well explained by Jenson, linear regression is to deal with continuous data that helped in predicting the future values on the basis of past data. Okay, but what is logistic regression? Logistic regression is little different. logic regression helps you in classification of binary. So what does I mean by classification in binary? If suppose you have to classify things, like if suppose you have to classify mail, either it is spam or not spam. So here you will create two classes. One is spam and other one is not spam. And the incoming mail that the mail comes the mail that you get, you will identify them in these two classes. Okay, so there are few many examples of it, like if it's cancer, then whether it's a benign or malignant. So do you guys remember such examples, or do you have any examples? Then please give. Hello guys, do you have some examples like that in which you can classify binary?
Election A and B person के लिए.
Yes. Obviously, that can also be considered as a example, but with certain boundary conditions. So in logic regression, we have two types of classifications. One is binary classification, and another one is multi-class classification. So what is binary classification and what is multi-class classification? We will learn as we go ahead. But we can I can say here that is we can use binary classification and multi-class classification. So what we can do is we can convert multi-class classification into binary classification and can run the algorithm multiple times. I hope you guys understood what I said. So now let's move ahead. Just a minute, guys. So as we saw in linear regression, we have our hypothesis. It was something like y equal to mx plus c type of thing. So similar thing we have in we have in logistic regression, but in logistic regression we have to remember that we have to classify it in two classes. One is 0 and other one is 1, like either it is spam or it is not spam. So for doing that, we have to build another function, because if suppose I take this same model of linear regression, we saw that value can go above about 10, about 20 also, but we don't want that thing here. So as you see here, the optimizer that was used in logic in our linear regression, what it was doing was we were starting from a point, and it was running to bring the error, optimize our algorithm by finding the global minimum or the local minimum. So guys, if I ask you what do you think, what can be the cases if I use linear regression instead of logical regression? In the cases, what can happen? Do you guys can give some examples, like what can be done? If not, okay, let me put a graph for you. So in this graph, you can see this was linear regression, this was logical regression. So now suppose if I have a model in which I have to predict whether it is whether number is 0 or whether the number is 1, or if suppose I take whether the class was spam or whether the class of emails was not spam. So if I train linear regression on it, what is linear regression? It was a line that was being plotted between two data points. So if the same line is plotted now on this data set, so what will happen is, if you can see in this example, there are few points that belongs to class 1 are towards the right side of this line, and there are few points that belong to class 1 are towards the left side of this point. So what happened here is there are this line also created two classes, but the two classes that it created are the left part and the right part. So we don't want that thing, as it will give a very bad result, or the model is highly inaccurate. So what we use is logic regression. What happens here is we have an S type of curve. What this curve does is, see, as you can see here, you can compare here the values of 1 that we had. Now they are above this curve, and the value of 0 is the class 0 that we have, they are below this curve. So here we can see that if the here the linear regression can predict the value of y that can exceed this range of 0 and 1, but the same thing will not happen in logistic regression. If I ask you why, then you can give this example in this, because in logistic regression we use sigmoidal function. So if I put any value of x here, like if suppose I put 102, then also the value the output value will be between 0 and 1. Okay, so that's the reason we use S curve in logistic regression. So if I say what hypothesis we should use in logistic regression, as in linear regression we use y equal to mx plus c. In logistic regression we use the sigmoidal function, as I just said, that if we use logistic regression, then we can plot in two different classes like 0 and 1. Hope you all understand till this point. If there is any doubt, you can ask. I assume no one is speaking. If you have any doubt, please speak. So I assume no one is speaking, so I will go ahead. So now the question comes, like as Jenson explained in linear regression, we have a cost function, the loss function or cost function. What the purpose of this cost function was to help our like our algorithm to get optimized. Okay, so for linear logistic regression, we can't use the same cost function that we use in linear regression. The reason, as we know, because if I put this sigmoidal function, this h of x value in this cost function here, if I put the value, the output that I will get is a non-convex type of function. And whereas in linear regression, we got a convex type of function. As you guys may remember, Jenson gave the example of convex type of relation. But if I put the same sigmoidal function value in this equation, in this cost function, if I put the value, if I plug in value here, I will get something because this contains terms like e to the power something. So this thing will give a non-convex type of function. So what will happen here is, if suppose I run my gradient descent algorithm, the optimizer I used, if I run this, there are high probability that I will get into a local minima. So what is local minimum? What is global minima? If I just take a minute. So this, as you can see, the most depth part of the whole graph is a global minima. So this so it's this point, and all others are local minima. So if suppose I use my optimizer function and I start my I start on this model, what will happen is, if I suppose I start from this point, the optimizer will give me this local minima as the best function, but what I needed was this global minima. So I hope that you guys understood what is global minima, what is local minima, and why we have to use therefore we have to use different cost function too. As now we got different sigmoidal function, this sigmoidal function we got. Similarly, we have to use different cost function too now, because this cost function is giving us a non-convex type of function, and we want a convex type of function. Because now, if suppose I take the same example, if I run my optimizer from here, it will get it will come to this, converge to this global minima only. So I will get this the output that I require. I hope you guys understood till this point.
Yeah.
Okay, so now let's move forward. So as I said, we have to use different cost function too. So the cost function that we use for logistic regression is somewhat kind of this. So it comes like it's a high mathematical thing that we have derived. So you can derive it for yourselves too, but it's very lengthy, and it includes very high mathematical terms. So we can directly plot directly put what the values are of cost function. So as I said, we have two classes in logistic regression, class 1 and class 0, like the predicted value 1 or predicted value 0. So for both the functions, we have different graphs. For the first one, that is minus log of h of theta of x, we have this blue curve, and for the second one, for 0, we have this orange curve. So to generalize this, like I have to generalize my cost function, correct? So for generalizing, what I do is I make a function that contains these both. So this is a generalized function. So if now I put value of y is y equal to 1 in this function. So if I put value equal to y equal to 1, this part will become 0, as you can see, and this part only will sustain. So, and as y is equal to 1, then the value will be minus log of h of theta of x. So it's the same value that we have here. Similarly for y equal to 0. So by doing this, we got a new cost function for logistic regression. Okay, so as gradient descent was explained by Jenson, the similar thing I will explain here. So what we do is, now after getting the cost function, we use gradient descent on it. So how we use gradient descent? So we just differentiate the cost function by the parameters in it, and this alpha. This alpha is the step, the constant value, the step. It is the size of step that we need to take. Like as it was explained by Jenson, if I take big steps, there are high possibility that I can miss this global minima, and I will go in zigzag manner, and I will never come to this minima. And if you take very small, then it might take very long time, and there are many other complexities with with alpha is very small. So we have to predict what alpha we should take, and there are few machine learning models too which give you this alpha value. So for now we can use heat and tile method, like we can put different values of alpha and we can find what was the best output that we were getting. So by running this as Jenson showed you that we ran it iterations were run, like 1,000 iterations were run, then we got a straight line like that thing. So similar thing is happening in logistic regression too. So by doing this, if I think now you have understood the gradient descent. Is there any doubt till now?
Nope.
Okay. So now I will move to multi-class classification. So as I talked about multi-class classification in the starting of our slide, I said that it can be converted into binary class classification and can be run multiple times. So if you see here, we have three classes: class 1 that is green color, class 2 that is blue color, and class 3 that is red color. So what we are doing now is what we are doing is we are converting this red color and this blue color both into one class, this like this thing, and now we have two classes, one is green and other one is blue. Similarly, like as we have three colors here, so we are doing this three times. Like first we will consider these two as blue, then we will consider these two as blue, and then we will consider these two as blue. So by doing this, we have converted a multi-class classification model into a binary classification model. And by doing this, like we can do optimize our machine learning model, and we can find like we can easily do the complexity will be decreased. So I hope till this point you have understood everything. If there is any doubt, you please ask. You guys can unmute your mics and ask. Is there any doubt? Should I move towards the coding path? Hello, is there any doubt till that point? Till this point?
No doubts.
Okay, so let's move to the coding part, like how we implement this in action, how we take this in action. So as I discussed what is logistic regression and what is different between linear regression and logistic regression. So this is like this is how linear regression model will work on a logistic regression problem. So we don't want that. So now let's talk about like how we will plot, how we will use linear logistic regression. So let's first see how the graph is, how the graph of a sigmoid graph looks of logistic regression. So it's something like as it was shown in the PPTs. Okay, so what I'm doing now is I'm taking the Titanic data set. What the data set contains is it contains the passenger of information that were on board on Titanic, and what we will do is we will now bifurcate passengers in two groups. One is survived and other one is not survived. Okay, so now let's first import our libraries. So as we see, our libraries have been imported. Then what we did was we first found what is included in our data set. So we found that there are passengers IDs, there are survival, there are class, their name, their sex, their age. So these are the few things that are in our data set. So just we like described in the tabular form. So as we can see that there were total passenger, there were total 891 passengers on board. We know the age of 714 passengers on board, and we know the fare of 891 passengers that were present on the board. Similarly, now what we will do is we will run our this is what these things we are doing is this is all called pre-processing, data pre-processing. So why we need to do this is we have to like we can't give all the parameters to our machine learning model. If we do so, our output that we expect won't be that good. So we have to draw few parameters like fare. Fare doesn't like directly bring your machine learning models to some conclusion like whether the person will survive or not survive. So for that thing, we will not consider fare. Similarly, there are few parameters as these are only 5 to 6 parameters, there are few parameters in the dataset that we have to drop, that we don't have to consider that parameters. So when we plot this, these are the this is the first five data of the dataset. So we have passenger ID, we have whether he survived or not survived. Then we have in which class he was traveling, his name, whether he was male or female, his age, and whether he had any spouse or sibling, and the ticket he bought. So as I said above, in this pre-processing we have to drop the data that are not so like important. So as I said, ticket and fare are not that important in your data set, like to predict whether the person will survive or not survive. So we have to like not include these parameters in our machine learning model. Similarly, as we go forward, we will look towards different other parameters too. So when I ran what I did is I ran the whole like as you can see here, it's written nan run. In cabin it is written nan and nan. So what does it mean is the data set of the data is missing for that person. So if I see for Mr. Owen, whatever his name is, his data for cabin is missing, like whether he was in cabin or in which cabin he was, that is missing. So I like found out how much percent of data was missing in different parameters, and then I plot them in the descending order. So I got that total 77.1% data of cabin was missing. So it's a clear indication that now we don't have to consider, we should not consider cabin in our machine learning parameters, because now if I consider cabin in my machine learning parameters, as there is high percent of data that is missing, the output that will be created by my machine learning model will be not the correct, will not be the correct one. Now, if I see age, it is only 19.9% missing, embarked from where he boarded the ship. So these are like 0.2 and 19.9% missing. So what we will do is we will not remove these things. What we will do is we will find the mean of this data set. Like in age, we have age of total number of age that we have, the person total age that we have, number of count of age that we have. We will find out that we will find the mean of all that count, and we will put the values in the place that where they are missing. So I hope you understood till this point of time, like till this you have understood. Okay.
Yeah.
Okay. So similarly, like what we did was so the same thing is written here, that cabin has 77% data missing, so we will drop that thing. And similarly, embark that is that it has only 0.2% data missing, so we can easily fill the field by finding the mean and putting it into the places where we have like missing values. So what I did now is I like found like what data I must include parameters I must include in my machine learning model. So first of all, like I plotted like in sex how many male that were on board and survived or whether they not survived, and how many female that were on board whether they survived or didn't survive. So if you see in the graph, it clearly shows that the number of females that were on board, large number of them survived, but on similarly on if you see the male graph, large number of didn't survive. So it indicates that this parameter, the sex parameter, can be used in our machine learning model. Similarly, we then plot about our classes, like as we know, Titanic contained these 3 classes: first class, second class, and third class. So then we plot whether the person who belongs to the first class, whether he survived or didn't survive, like how much people were present and how much of them were survived. So we found it is clearly dependent on classes. As you can see here, the people who were present in class 1 survived the most, and the people who were present in class 3, they survived the least. So we can include this parameter also in our machine learning model to increase the accuracy of a machine learning model. Then what we did was, as we know that machine learning model that we want to train, it will not understand like male, whether it is male or whether it is female. We have to give some binary to it. So what we do is we then first find whether the person who was traveling on the ship whether he was alone or whether he was with someone like his sibling, his spouse, or whether he was with his parents. So what I did is I ran through the whole data set, and I like labeled, if the person was alone, then I labeled him 1, and if the person was not alone, then I labeled him 0. So I got the count like this many persons were alone and this many persons were traveling with someone, like with some of their relatives. Similarly, now as I said above, the passenger ID and cabin, as cabin data set was missing, the 77% data of cabin was missing, and passenger ID, as we know that passenger ID will not contribute to like whether you will survive or not survive. So we have to drop this data because it will bring the accuracy of a machine learning model down. So what we did is we dropped this data set, drop this. So we will not consider these parameters in our machine learning models. Then what we did was we saw that in age 19% data was missing. So we found the mean of all the ages that we have, and then we filled that values in the places where the data set was missing. So after doing that, this function np.random.randit helped me in doing that. And after doing that, when I ran the loop, I saw that 0. Now there is no data set in age that is missing. Like we all the ages, like corresponding ages to the passenger traveling in the ship, we know their ages. So similarly for we did for embarked, like where the person embarked from, like it might happen that ship did not came to that point, and the person who has to board the ship at that point, like if suppose I have to board the ship at S and the ship collapsed at C point, so that thing will like affect our model. So we found that also, like how many embarked, what was the mean of the embarked, like many of them embarked from S point. So similarly, what we did was, as 0.2 data set was missing for embarked, percent data set was missing for embarkment, we filled with the common value S, as many of them like boarded the ship from S. So by doing that, now if you see here, the survived, like number of count we know of survived people was 891. As you can see at age now, the age the 19.1% data set was missing, but now we have all the data of the people present on the ship. So like we figure, like we pre-process everything Now what we will do is, now we will drop few more parameters like ticket. Ticket doesn't matter whether you will survive or not. Your name doesn't matter. So we drop all that parameters. Then we convert it, like give male as 0 and female as 1. As I said, that in machine learning model, the machine will not understand whether if you are giving him male or female. It will understand binary. So we gave him 0 and 1. Like we gave male 0 and female 1. Similarly, for embarked, we give if the point was S. If someone embarked from S, the point was we gave it 0. If someone boarded ship from C point, then we gave 1, and if someone boarded the ship from Q point, then we gave it 2. So after that, similarly, what we did was we found that in the age also, there were some age groups in which the people survived the most, like the young ones or the old one. They survived the more. So that to find whether the person who belongs to which age group and which age group people survive the most, we bifurcated the age groups. Like from 11 to 18, we gave as 1. 18 to 22, we gave as 2. So after plotting it, we found that the age group 4, that was the predominant one. 174 people were present in the fourth age group. And as you can see here, the fourth age group belongs to 27 to the 33 age. The people who are from 27 to 33 age were in the fourth age group. So after doing this, when I plotted my the table, so you can see here everything is now binary. So this fair we have to drop. Like we don't need this fair. So what we'll do is we will drop this fair too, and what we'll do is we will remove survived from here, from our x train. Like we not now we will create two axes. One is y-axis and another one is x-axis. So we will remove survive from our x-axis and we will give it to the y-axis. So the value of our machine learning predicts from x-axis whether it matches with the y-axis. It will give the accuracy of our model. So similarly, after doing that, for testing too, like in testing too, after training our model, we need some data set to be tested on that model too. So for that also, we drop the parameters like personality, cabin, and fare. And after doing that, this is how my training data set looks like. It contains a class in which the person was traveling, the age of the person, whether he was male or female, the age group in which he belongs to, whether he was traveling with someone or he was alone, from where he embarked, he embarked from S location, C location, or Q location. So in this way, this is our training data set and this is our testing data set. So what we did was we used a sklearn feature, sklearn library that gave us logistic regression directly. So what we did was we fit our model extend and widen, and after that we found the accuracy of our model. So we got it 80.1. The accuracy of model is 80.1%. So we were able to detect 80% correctly whether the person will survive or not survive. I hope till this point everything is clear. If you have any doubts, then you can please unmute your mic and ask. Is there any doubt till this point of time? Oh, so I assume there is no doubt. So I will move ahead. So what we did was we cross.
Someone has raised their hand.
Okay, you can go ahead. You can please ask your doubt. You can unmute yourself.
Why aren't we using our validation set? I mean, the models that I have trained so far, I use a training set, I use my validation set, and then I use a test set. I divide my data set into 3 parts. So why aren't we doing that here?
See, it depends how big data set you have. So as you said, you might be having a small data set, so you are dividing your data set in testing and training part, correct? But if you have a large data set, what we can do is we can keep some part reserved for training and we can keep some part reserved for testing. Okay, but here, as you can see here, I have used cross validation too. Like I have used cross validation. So for using my training data set only, for testing, I have did that thing too. I hope I answered your doubt.
Yeah.
Okay. So I will move ahead with this. So as I said now, we generated a score of all.
One more doubt is there. Kazim also has one.
Yes, please go ahead.
सर जो आपने जो रिजल्ट प्रिंट किया था जिसमें 1 2 3 वो सिर्फ विजुअल पर्पसेस के लिए था कि कुछ रीजन है?
देखो इसका so as this thing you're asking, these things, not train and testing head.
Yes sir.
So the thing is, this will go in our machine learning model. Our machine will be trained on these models. So this is our training model. Our machine will be will be trained on this model. So if you use here, like if you you write here male, female, so it will be very difficult for a machine learning model to understand what it was, and it will be very difficult for the machine learning model to find the relations. But when I use binary numbers like binary 1, 2, and 3, 0, 1, so it will be very helpful for machine to establish the relations between the training data set. Understood?
Yes, sir. Thank you.
Okay, so that's the reason we used it. We use it because if you see here 0, if I write in age, if I in sex I write 0, you won't understand whether what 0 means. But here 0 implies female and 1 implies male. So that's the thing that we are doing here. Like machine will help. It will help machine to understand, to establish a relation between the training data sets. So after this, if is there anyone who has any doubt, or should I move forward? So I suppose now there are no hand raised, so I will move forward. So here you can see that I have used I have generated a score. What this score is, this is this is a predicted value, like the things that we used here, the parameters that we used here. Just a minute, I will show the parameters to you. The parameters that we used here, how much accurate the parameter was with with the real data set. So this is the array of that thing. We have mean like how it is 80, like approximately 80%. So that was how much our model was able to predict, and we have standard deviation, how much our model was deviated from the real model. So after that we run our model on our testing data set that we created here, exhaust test, and then we can see an array of numbers here. The array of number we can see. So as you can see here, it is 0. That means he might have survived or not survived. 1, he might have survived or not survived. So it is representing that thing. So I hope till here everything is clear, and if there is any doubt, you guys can mute and ask. Is there any doubt till this point? If not, then I will ask Riya to continue the session with the new topic, the next topic. So Riya, yes, please, you can continue.
Yeah, thank you, Shubham. So hi everyone, this is Riya, and I'm a community mentor at SMLRA. So just a second. I hope my screen is visible.
Yes.
Yeah.
Okay. Yeah. So I'll be taking up the topic knife-based classifier, and yeah, so machine learning is fundamentally the art of prediction, and it's just about hitting that spot between timing and accuracy. So we move on to the topic knife-based classifier. The knife-based classifier has been successful for many purposes, but it works particularly well with natural language processing problems. So one very common problem we can solve with this is filtering out spam and non-spam messages or emails. We can use, so machine learning also falls into two categories, that is supervised and unsupervised learning. Supervised learning again falls into two categories, that is classification and regression. Knife-based algorithm falls under classification because we are basically classifying two different types of the whatever the answer we want. It's actually based on two types, right? So where is it used? The knife-based has its applications in the first one is face recognition. So it's basically used to identify the facial features like eyes, nose, mouth. The knife-based has a very good application here. It can be used to predict weather, where it can be like the answer will be whether the weather will be good or bad based on different parameters like temperature, and it will just tell us the probability if it will rain or not. It can be used well for medical diagnosis, like doctors can diagnose a patient and using the information that the classifier provides, healthcare professionals can use the knife base to indicate if a patient is at a high risk for certain diseases like heart disease, cancer, and other ailments. Also, it's used for news classifications where Google News recognizes whether the news is political, world, domestic, or so on and so forth. Yeah, so So what's so naive about naive-Bayes theorem? The naive-Bayes theorem is called naive because the basic assumption, the underlying assumption it makes is that the features are independent of each other, the parameters, which is not always the case. So it's not a very strong theorem, but it's good for many other applications. So yeah, it has a good purpose. So we need to know this formula first. This is called the posterior, that is the probability of A being given that B is true. This is called the likelihood, the probability of B being true given that A is true. This is called the prior, that is the probability of A being true, and this is the probability of B being true. So yeah, so this is the exact same formula. And yeah, so this is a very basic example, like I think which most of us have studied in school or high school. So the problem we start with is a card is picked from a deck at random. The objective is to find the probability of a king, given that the card picked is red in color. So this is what we are supposed to find here: probability of it being a king, given that the card pick is red in color. So we use the same formula again, the one we used here. So probability of it being a king, given that a red card, it's that we just reverse this, that the probability of being a red card, given that it's a king, into the probability of it being a king divided by probability of it being a red card. Okay, so yeah, so probability of getting a red card, given that the card chosen is a king, is that we have two red kings, and there are two red kings and there are four total kings. So this probability is half. The probability of it being a king is we have 4 out of 52 cards, so that's 1 by 13. Probability of it being a red card is we have 26 red cards, so that is again 1 by 2 out of 52. And hence finding the posterior probability, which is what we were supposed to find, that is a probability of randomly choosing a king, given that a card is red, is we get this, we apply the same formula here, we multiply this, and we get 1 by 13 or 0.07. So this is the basic formula here that we have almost everyone has studied in school. So yeah, so when it comes to naive Bayes, there are 3 basic types. The first one is the Gaussian naive Bayes. So this is basically an extension of naive Bayes. So all other functions can be used to estimate the distribution or the data, but Gaussian only uses normal distribution. It's the easiest to work with because like you only need to estimate the mean and standard deviation from the training data. So if we have some variables which do not have this property, then we have to transform the variables accordingly to use Gaussian naive Bayes. So this is the formula we can calculate it from. The parameters sigma y and mu y are estimated using the maximum likelihood problem. So what is maximum likelihood? It's an estimation method that determines values for parameters of a model. So the parameter values are found such that they maximize the likelihood that the process described by the model produced the data that were actually observed. So yeah, so we use this formula for Gaussian naive Bayes. We'll use a very simple example for that, and yeah, this is how we implement the Gaussian naive. So we import the basic libraries, that is NumPy, Pandas, sklearn, and Matplotlib. We have read this data set, which is a diabetes data set, and we are going to predict if a person has diabetes or not. So this is the glucose, this is the blood pressure, and we can predict if a person has diabetes. So yeah, so we can see this data set. We drop the diabetes column to like that is the dependent variable, so that will be y. We split the data set into testing and training. So the test size is 25. We have kept it at 25%, and the random state is 1. So what random state means is it's used as to set the seed for a random generator, so that we can ensure that the results we get can be reproduced. So see, because we split the data at a very random technique, sometimes when we use the testing and splitting without the random state, we can get different values every time. So like now if I ask someone to give me 5 values from numbers 1 to 25, so people might come up with different values. So to use, like, if we want to use random state, it ensures that it comes up with the same values every time and not 2, 3, 4, 5 ones and 7, 8, 1, 7, 8, 9, 10 again. So we just want the same output every time. So we use random state. Here we are implying which model we are using. So that is Gaussian knife based. We fit the model into testing and with the training data set, and we predict the model. So this is our prediction from the testing data set, and we get the accuracy as 94%, which is really good. So we can see that the Gaussian knife based theorem is a really good algorithm for small data sets. And yeah, so we can move ahead with the next one. Yeah. So next is the multinomial knife based theorem. Multinomial is mostly used for NLP problems. To classify a message as spam or not spam, we consider a few words such as friend, lunch, dinner, bell, etc. We count the frequency of those. In a like this, if these words are present, it's possible that it's from a friend or a colleague or a family member. But there are words which are always used in spam messages, like congratulations, you've won a lottery. Those messages are usually classified as spam. This is not the only way to classify them as spam, because also your friends could be congratulating you on something. But yeah, so this is one basic technique the multinomial knife based theorem uses. So yeah, so exactly. So in such a case, we have a frequency as a feature. In such a scenario, we use multinomial knife based theorem. It ignores the non-occurrence of features. So if we have a frequency 0, then the probability of occurrence of that feature will be 0. Hence, multinomial knife based ignores that feature. So it is only used. It's mostly used to classify text-based problems. Yeah. So we can move on to the example. So yeah, so this is the small data set we'll be using. This is a hard-coded data set. So if you are classifying a review as positive or negative for a movie, so if it's I like a movie, it will be positive. But sadly boring ending, that will be a negative review, right? Sad and boring movie is again a negative review. So suppose we have to classify this sentence, overall like the movie. So how would we classify that as positive or negative? So this is the technique we use. We use multinomial knife based theorem here. So we calculate both the probabilities, the probability of overall like the movie being positive and the probability of overall like the movie being negative. So we remove stop words and stemming. So what is removing the stop words? So words like the, they are not important for our data set. So we might as well just remove them. Next is using stemming. Now, stemming is taking out the root of the word. Like if we have two words, pythonly and pythoned, so the root of the word is python, right? So that is how we can just take out the root of the words. And yeah, so we use feature engineering. We need to convert these texts into numbers and we can do calculations on it. So we use this theorem to calculate the probability of this sentence being positive. So by using the knife-based theorem again, probability of overall like the movie given positive into probability of it being positive and upon the probability of overall like the movie. Okay. So so what we do is first we calculate the priority probability of each tag. So what we use is the probability that this is positive. Like in the data set, we can see we have 3 positive, right? So that is our first probability. Then the probability of being negative is 2 by 5. As you can see in the data set, so there are 2 negative reviews. And yeah, so so then calculating the probability of the word overall being positive means counting how many times the word overall appears in positive text. That is 1. And divided by the total number of words in positive, that is 70, right? So therefore, the probability of overall given positive is 1 by 17, and the probability of liked positive. So because we have 2 words, right? Overall liked the movie. So these are the words that matter. And the is a stop word, so we have removed it. So we need to calculate probability for 3 words, that is overall, liked, and movie. So we get 1 by 17, 2 by 17, and 3 by 17 respectively. If the probability comes out to be 0, we need to use a method called Laplace smoothing. That is adding 1 to every count so that it's never 0, because 0 probability doesn't make any sense. And to again balance this, we add the number of possible words to the divisor so that the division is never greater than 1. In our case, the total possible words are 21. So now we calculate this probability, the probability of the word overall being positive, the probability of the word liked given it's positive, and the probability of the word the given it's positive, and yes, probability of the word given movie it's positive, and into the probability of all of them being positive. So that comes out to be 0.00013. So yeah, so and this is the probability of it being negative. My bad. This is the probability of it being positive. So we get that the probability of it being positive is greater than negative. So we classify this review overall like the movie as positive. So this is how we implement it here. We import the basic libraries. We have hard coded the data set here. The data set has 2 columns, that is the text and reviews. We perform basic data pre-processing here, that is just not let the program confuse because of upper and lower case. So we do that basic data pre-processing. We use a counter vectorizer, which is used to transform a given text into a vector on basis of the frequency of each word count that enters that occurs in the entire text. So we fit it to an array. Now now we import the multinomial naive from sklearn library. When we fit it, and so this is our confusion matrix. What confusion matrix is that it is basically an n cross n matrix used for evaluating the performance of a classification model. N is the number of target classes. So yeah, here you can see that we get true positive, false negatives, and true negatives. So this is what we've got here. Yeah, so this was our multinomial naive based. We move on to the next one. Does anyone have any questions? We move on to Bernoulli naive based theorem. So this can only be used when the features are binary. So instead of using the frequency of a word, we need to have discrete features, that is ones and zeros, true and false. Likewise, it should always be in a dichotomy. So in this case, the feature that will be used only if they are binary, we can use it in naive base. And it follows this principle, the Bernoulli distribution. So yeah, so see, as we deal with binary values, we consider P as a probability of success and Q as a probability of failure. So we get Q is 1 minus P. So X can only have 2 values, that is 0 and 1. Now here, we again consider an example. So just a second. Yeah. So we need to classify if a student who is confident, he has studied and is not sick, will he pass or fail? So this was the data set we used for training. First, we'll calculate the probability of how many, like the total passes and the total failures. So we get 3 by 5 because we have 3 passes and 2 failures. So the probability of him being confident is yes, given that he has passed is 2 by 3. We calculate all the basic probabilities first. Study being yes, and given that the result has passed is 2 by 3. And for sick and pass, it is again 1 by 3. Similarly, we calculate it for fail also, because only if we compare the 2 probabilities, we can get which one is higher and we can classify it accordingly. So again, we classify this as if he's confident has failed this, if he has studied and still has failed, and if he is sick and still has failed. So we use this for that, and we calculate the next result, that is if he has passed, like if the result has passed into probability that the result is passed. So we get this for the first one. The next one will be the probability of X, given that the result is failure, into the probability of result being failure, that is 0.05. So now the next step is to calculate the probability of estimator. That is, we need to calculate the P of X. So when we calculate P of X, we get the answer as 0.144. And then we can finally input these values here, which can be, which gives us if he has passed or failed. So X is basically calculated everything, all the parameters, it has kept in mind all the parameters here, and it's calculated. And finally, if we can get a result, if he has passed or failed given on these parameters. So here we can say that he has failed has a probability 0.34, and the probability that he has passed is 0.611. We can say definitely that the guy has passed. So now we'll just see a small example for this. Yeah, so we import the basic libraries. Here we have only used very random values, like we'll be having a training data with 500 instances, 10 features each, and it will have only binary values, that is ones and zeros. So we classify it as the X test and Y tests are from, they're classified here. We import the Bernoulli knife-Bayes theorem's algorithm from sklearn, and yeah, when we fit the data and predict the model, we get the accuracy score is 0.64. That's fine because the model is quite like we have a small data set, not exactly small, but given the pre-processing and all which is not done, 0.64 can be classified as a decently good accuracy score. Next, we move on to difference, the basic difference between Bernoulli, multinomial, and Gaussian knife-Bayes. So multinomial considers a feature vector where the given terms are present only the number of times. Like as we said, we discussed that it's a frequency, it uses the frequency of words. So on the other hand, Bernoulli is a binary algorithm, which calculates only if the feature is present or not. And Gaussian is Gaussian is based on a continuous distribution, that is normal distribution. So yeah, so multinomial is used for classifier problems. Bernoulli is used for only discrete data, and Gaussian is used when we are dealing with continuous data, and it uses Gaussian distribution. The basic advantages and disadvantages, we'll go through them quickly. The algorithm, this is for knife-based, okay? The algorithm works quickly and can save a lot of time, as we saw. The knife-based is suitable for solving multi-class prediction problems as well. If its assumption of independence of features holds true, it can perform better than other models, which is exactly why it's called knife-based, because there are very few examples where the parameters are independent of each other. The knife-based is better suited for categorical input variables than numerical variables. The disadvantages are it assumes that all predictors are independent, rarely happening. That's something that rarely happens in real life. This limits the applicability of this algorithm in real-world usages. The algorithm faces the zero frequency problem where it assigns zero probability to a categorical data. That's exactly why we had to use the Laplace smoothing technique to overcome this issue. Its estimation can be wrong in some cases, so we shouldn't take the probability outputs very seriously. Okay. If anyone has any questions. Okay, thank you. Jatin, you can take over.
Yeah, sure.
Hey, may I ask one question?
Yeah, go ahead.
First question is, what is the linear regression, how it is different from logistic regression, and why you taken this neo-based algorithms? Means 3 topics, at the same time. So what is the reason behind this? You take this one first of all on linear regression, and you're not giving idea on probably. I think so. Audience has come to know a lot of things, but one thing observed that in a mathematical formulation regarding linear regression. Is it not clear? So I think so.
I'm sorry. What is not clear?
Linear regression you take first, right? And then logistic regression. See, what are the difference between linear regression and classification? Why you use regression? That was a question from the audience side.
Yeah. So basically in logistic regression, we'll be predicting a continuous value that will be the probability. Okay. So we're basically using regression, but at the end, we'll select a threshold of whether it goes like what threshold value of the probability will go as positive and what will be negative. So it's actually at the end product, it's a classification problem. But
I have seen that one. I have seen that one.
Yeah.
I understand that one. But question would be there, a linear regression. Suppose somebody starts here, because number of our newcomers here, I think so. Now, and they want to start some sample program. You give some farm example. And if you want to start somewhere with a basic example, it will be basic example for linear regression is petrol pricing, or you can so give the for housing prices, so and so. So in that case, if you give them some example like housing prices, let it be this is a famous example.
Yeah.
Then it is
very famous.
It's a very good for understanding the basic parameters.
Yeah.
How do we come that one? If you give the idea, then it is more clear in theoretical point of view, right?
Yes.
And that same things you like to go to the gradient descent. And the gradient descent concept would be there too much required, but why you require that one? That is link should be there. I think it is miss someone, so it's a somewhat it gives the not certain what exactly this audience or everybody say yes I understood, but but real point of view, how do we implement that one? That is the question, because something Python gives Python gives a lot of libraries. I anticipate this one, and but something you have to take the practical an example and solve it. It is good, very good input from my side, I think so.
Yeah,
you take
we appreciate it. Yeah, we appreciate it. You can also visit our the collab notebooks in the GitHub, and there you'll see all the practical examples for each algorithm. So
see, I
GitHub
got
notebook is there,
this in 2016, and that time I have given example as well as solution for this one. I have ready with this one actually, but I can't show you this one. But I listen because this is refreshing for me actually. So lot of things will be there. I like to share, but bit of time I can't say
Are you
anything
on
here.
Discord? Are you on Discord? You can share your solution or whatever discussions there are in Discord. We have a community there.
Yeah, this is the problem actually. I thought yesterday I done this one, I didn't get properly discount what exactly would be there. So I'm happy with the teams actually. Okay, I will go through it, and we'll definitely give you a solution about this one.
Okay, surely. Thank you. Does anybody have any other doubts?
No.
Yeah, so we can just take a small break here, just 2 minutes, because we have been learning linear regression, logistic regression, and linear bias. Now we'll move on to k-means algorithm, k-means clustering algorithm. So because k-means clustering algorithm is an unsupervised learning algorithm, we'll let everyone settle in, take a small break, drink water, your time. In about 1 minute, we'll start. By that time, people can go on to the Git and go to k-means, press this k-means notebook, and if you load, select this, open in Colab. Because k-means is an incredibly visual and intuitive algorithm, this Colab notebook has a lot of matplotlib functions that will help you visualize each of the steps very clearly. Okay, so by the time the break time finishes, please download or make a copy. Basically, I want you to code along with me. If anybody is having any doubts or any problems in downloading or like opening in Colab, they can put it in chat or unmute their microphones. All right, I hope everyone's back. Again, as I said, K-means clustering algorithm is an extremely visual and intuitive algorithm. So please go ahead and open up this notebook. If everyone has done that, we can start. So before we move on to K-means clustering algorithm, as I said before, K-means clustering is a type of unsupervised learning problem, right? What is unsupervised learning? It's basically an algorithm's ability to analyze unlabeled data. You can see in this very simple example here, we have apples and watermelons, but the model doesn't know that. Or what it's trying to do is basically discover hidden patterns without the need of human intervention. So basically grouping these two together, not together, separately, like apples and watermelons. This type of learning is very ideal for data analysis, customer segmentation, and image recognition. A subset in unsupervised learning is clustering. Clustering is a very popular data mining technique. And now this statement is very important. Clustering is grouping up similar points. I'm going to be using this statement a lot, right? So there are many different types of clustering. Today, we're going to be focusing on the hard clustering or the exclusive clustering, where each sample can only belong to one cluster. So K-means has two parts in its name, right? K and means. What is K? K is the number of clusters that you're aiming for. So in this particular graph, there are 3 clusters, right? Now the next obvious doubt will most probably be, how do we select K when the data is not as visually easy to understand? We'll learn about that in this in the notebook. We have many ways to optimize and choose the optimal value of K. The next part, the means. See, I told you before, clustering is a way to group similar data points. In K-means algorithm, the measure of similarity will be distance. We're going to be dealing with the means and the centroids of the clusters. Let's move on to the K-means notebook. Make sure you connect and import the basic libraries. Everyone should be following along with me. Now, this is my custom dataset that I created using make blobs. When you're editing this, make sure to change these 2 values, right? So here I can make 4 and run it. And as you can see, I'm getting 4 clusters here. Make sure to also change this so you can get some different data set to work upon so that you can learn from my example and your example. You'll get a better foundation for not only K-means, but also clustering in general. So yeah, I'm going to be working with 5 centers. Hopefully everyone has taken different centers and different random states. Usually, if you don't understand what a variable is here in these functions, you can just print them out. And if you still have doubts regarding a certain variable, you can enter it in chat or unmute your microphone. Before we start with the steps for the algorithm, I want everyone to properly understand what's the main step in the algorithm. That is distance calculation. So you can just play around with this basic code, run this function first. You can play around with this basic code, choose whatever index you want. And run it. So basically it's basically a visual way to represent distance between them. It's 7.26. This is the step that's going to happen a lot. And the reason I kept this here is because while explaining the steps, I'll refer to this again and again. So let's start with the steps for the algorithm. Right? The first step is to initialize k random centroids. Right? So if I run this cell. Oh yeah, I didn't define n. Make sure you define n. And I run this. You see, these red points are my random centroids, initial centroids, right? Right now, the centroids are too close to each other. That's why this is not an optimal initialization, but I'm going to work with this so that we can see how to improve it too, right? So these are my initial centroids. We're going to be working with these ones. Next step is to calculate the distance from each data point to these centroids. So let's imagine that this lower yellow point is the data point and this upper yellow point is the centroid. We're going to do this red line for each of the centroids. That's the step 2. So run it. The minimum variable will store the the cluster that that data point belongs to. So the first data point is closest to the first centroid. The second data point is closest to the third centroid, and so on and so forth. In the third step, we'll just create a dictionary. You can see here, one basic dictionary, and we'll assign based on this minimum variable. If I just run this cell, you can see the clusters are starting to form. As you can see, the purple data points are closest to this yellow centroids, and like basically for each color, right? Green is closest to this one. Now this is the first iteration only. That's why it's not looking the most optimal. The step 4 will be to update the centroids. Remember, centroids, well, they're centroids, so they should be in the center of the cluster. So I'll just replace the centroids with the means of the cluster. np.mean calculates the mean. And this is how the centroids are shifting. See, this yellow one went here. So it's all the clusters are going from yellow to black. This is a shift in the centroids. These 4 steps define the first iteration of the algorithm. Now what our job is to repeat the steps 2 to 4 until the centroid keeps changing or till we hit the max number of iterations. So to revise it again, this is a simple flow chart, right? We'll start, we'll input the number of clusters that we want. Next, we'll initialize k random cluster centroids. Then we'll get distance from each point to these centroids. In the notebook, I used a 2-feature example, that is a 2D example, but you can do it for n features and n dimensions also with this formula. After getting the distance from each point to centroids, we'll cluster data to the closest centroid. Then again, we'll recalculate the centroid. And lastly, we'll check if the centroid has changed. If it has, repeat steps 2 to 4. If it has not, then, well, that's our initial algorithm. If I can just iterate over the process for 50 iterations, this is my final result. Now you can see that this is not looking great. That's because of our bad initialization. We'll tackle how to optimize the clustering in the later sessions. But what I want to ask is, do you have any doubts in this first 5 steps? Flowchart is here for the algorithm. Anyone has any doubts in these first 5 steps? I'll just check the chat also. Okay. So if anybody has any doubts, they can clear right now. If not, then we can move on to the most, I would say the most important part of my presentation, evaluating clusters. Now remember, this is an unsupervised learning problem. In the previous algorithms, you saw that there were always labels that you could use to calculate the loss or the error. Here, we don't have any labels. So we cannot calculate a loss function. We cannot. So how do we evaluate what clustering is the best? Right. So here is a very simple 1D example. These 12 data points are aligned in this way. And I want you to put in chat or unmute yourself and say which of these options is the best clustering. The colors represent the clusters themselves. Anyone? Can anyone answer? This is a very simple 1D example. We have A, B, and C.
I think unmute and speak.
Yeah, I think the second one is the best cluster because it is uniformly distributed.
B.
Yeah.
Yes.
Perfect. Uniformly distributed. That's what I wanted to hear. So remember, because we don't have a direct loss function, we're going to have to work with variance to determine which clustering is the best. Now, I said this before, clustering is a way to group similar points. As similarity goes up, variance goes down. But we can't have one cluster with really low variance and one cluster with really high variance. That is the case with A and C, right? The green and the red clusters here have too much variance. We want a well-distributed minimum variance in each of the clusters. That's where WCSS comes from. Okay, yeah, I forgot. The length of these lines, color lines, represent the distribution basically, their variance. That's why I combine them all. And from this, you can theoretically say, not intuitively, theoretically say that D was the best option. Yeah, as I said, now that we know that we're going to use variance as a way to evaluate our clusters, the method for calculating variance in this particular case will be WCSS, within cluster sum of squares. The name says it all. What it does is that it calculates the sum of squares from the centroid to each data point for each cluster. The formula is here. It's pretty simple. If anybody has any doubts on this particular part of variance and WCSS, please speak up, because this is the most important part of k-means clustering algorithm of deciding how to evaluate unsupervised problems, right? If nobody has any doubts, we can move on. Now that we know the concept of WCSS and like how to calculate variance, we can now tackle our initial question of how do we select the best or the most optimal value of k. Moving on here. Yeah, we're going to be using elbow method. Now you may ask me why elbow method? Well, one disadvantage of using variance as an evaluation method is that if we keep on increasing the number of clusters, then the variance will obviously keep on decreasing. If I say I have 100 data points and I want to make 100 clusters, then the variance will be 0. That doesn't really make any logical sense. So what we're going to use is we're going to use elbow method, and the plot of the elbow method will be something like this. Main reason why we are using elbow method is so that we can like visualize where the most significant change in WCSS or variance occurs. So here at 5, you can see that's the last corner point, and this graph also looks like the elbow, right? The hand, and the point at 5 represents the elbow of the hand. So 5 is the most optimal value here, simply because that's the point after which there is no significant decrease in the variance. So how do we use the elbow method? The answer is pretty simple. Perform k-means clustering for different values of k, ranging from 1 to upper limit. Here, the upper limit is 10. 9 range goes from n-1. So the upper limit here is 10. We'll calculate k for each. Sorry, we'll calculate WCSS for each k. So from one cluster, clustering 1, 2, 3, we'll calculate WCSS and we'll plot it. Then we'll visualize the graph and we'll look for the last corner point. I hope nobody has any doubts in that. If you have, please speak up or put in the chat. Just check once if there's any chat. The collab notebook link is in the GitHub. If Rahil can share it again, that will be great. Yeah. Thank you, Rahil. Also, yeah, the recording will be shared. It will be uploaded on YouTube, and you can watch it there as well. So, yeah, moving on. We have been using clustering on 2D samples for it to be easily visualized. Clustering can also happen on n features. Like this is a common example for 3 features. Clustering here. Countering the problem we faced here, like when we are doing the first iteration, we faced this problem, right? Here, the purple should be distributed in 2 different clusters, and this red and orange should be 1 cluster, right? How do we fix that? Well, to fix that, we'll use k-means plus. K-means plus is very simple. So let's say my first data point is this blue centroid. My first centroid is here, right? I'll select that first centroid randomly. Then the probability of the second centroid being chosen as a data point will be directly proportional to the distance between them. So let's say from this yellow point to this yellow point, the probability will be like a half. So from this yellow point to the yellow point of the green cluster, the probability will be even more because the distance is greater. So this is more probable of being chosen as a centroid. TLDR, what it does is that it picks up centroids that are far away from each other. This increases the chances of initially picking up the centroids that lie in different clusters. that's the end of the code from scratch and theory part. We're going to be working with real world case here quickly. By the time I upload the data set, people can ask any doubts that they have. The link to dataset is here. You can just download it from by clicking this link.
सर आपने कुछ वेरिएंस के बारे में कुछ बोला था, वो पार्ट में वो समझा नहीं.
Okay, I'll repeat. Don't worry. So, why do we use variance? Because this is an unsupervised learning problem, right? In supervised learning cases such as linear regression or logistic regression, we had an actual label or the true value with which we can calculate error. Here we cannot calculate error, right? So here we'll use variance. Why do we use variance? Because that goes back to our definition of clustering. Remember, as the similarity goes up, variance goes down. So basically what we're trying to do is minimize the variance across all clusters. Okay, that's the whole gist. And how do we calculate variance? With WCSS. Does that answer your question?
Yes, sir.
Okay. Anybody else? So here I imported a data set. I'm going to choose these two values, the annual income and the spending score. I'm going to plot it. This is our data set. Intuitively, I can say that there should be 5 clusters, but let's see. We're going to work with the same code that we have done before. I did not import k-means. Just wait. Yeah, let's run this. And yeah. This is our Alpo plot, and you can see, as I said before, with intuition, the number of clusters k is equals to 5 was our last corner point, and thus that will be the optimal value for this k-means clustering algorithm. Now that we know that the most optimal value is 5, we can just rerun the algorithm and fit predict our x labels. This is our final output. Now we have done everything except the WCSS part from scratch. So a fun homework for you guys would be to code the WCSS. You already have the formula here, I believe. Yeah, this is the formula. A fun home activity would be to code this from scratch. You can refer to all of the other from scratch code here. All of this you can refer and try and create a function that can calculate WCSS of one singular cluster. After that, you can put this instead of here in this line. If you can do that, that will prove that you fully understood what k-means algorithm is and how the concept of evaluating unsupervised learning problems is. That's the end of my session. Thank you. You can refer to all of the references here for more further information. Anybody has any doubts? Yeah, put a yes or no in chat or just unmute. If not, we can move on with SVMs that will be taken up by Burhanuddin.
So,
yeah.
क्या नाम है कोई आउटलायर से k-means काफी skewed हो सकता है centroid?
Yes. K-means is very susceptible to outliers, but as you increase the number of iterations and if you what do you call, use the k-means plus initialization, right, where you initialize centroids far away from each other, it will try and counter the outliers as well. So k-means plus is a must for every iteration of k-means that you're doing.
Thank you.
Okay, that's a good question. Anybody else? All right. So if there's no more doubts, Burhanuddin can take the stage.
Jatin, can you stop sharing? Yeah.
Yeah, I did.
So is my screen visible?
Yes.
Am I
Yes.
audible?
Yes.
Yeah, okay. So let's get started. I am Burhanuddin. I am a community mentor in SMLRA. I know that this session has been dragging on for quite some time, so we all might not be in the mood, but I'll try to make this really interesting. So I'm going to talk about SVMs. SVMs stand for support vector machines. So now what exactly is a support vector machine? It's basically one of the most powerful and versatile machine learning model that's capable of performing both a linear and non-linear classification, regression, and even outlier detection. It's like one of the most popular models in machine learning, and anyone interested in machine learning should probably give it a try. Now, how the logic behind SVMs actually works is, as you saw in the previous sessions, how logistic regression or linear regression, they basically try to predict an output, and then they try to minimize distance between the predicted output and the real output. But what SVMs do is they try to create a decision boundary and then try to maximize the width between the two different classes. So this is mainly done on data that is linearly separable. So like as you can see in this figure on the right, the dots in blue are class 1 while the dots in red are class 2. So now out of these three lines L1, L2 and L3, what do you think is the best decision boundary? Like what line splits the two classes the best? Like does anybody want to answer? L3, yes, that's correct. The reason being that is that one of the main training objectives of SVMs is to try to keep the two classes equidistant from the street that will form, while also maximizing the width of the street. Now, as you can see here, these are some other decision boundaries. As you can see, these on the left plot, this red, purple and green boundaries, they're actually not that great. They don't split it clearly, and even if they do, some instances are very close. So in generalization terms, it might not generalize so well. But on the right plot, you can see that the decision boundary is a dark line, and the dotted lines are actually the support vectors. So now what exactly are the support vectors? The support vectors are basically just instances of the two classes that are closest to this decision boundary. They are basically used to form to determine the width of this street. Like the objective function is to maximize this street while keeping these two things equidistant. All right. So as you can see, this is perfectly well defined. Like any instance that is on this side of the street is class 1. Any instance that is on this side of the street is class 2. So now this is the basic how SVMs work, but there's some other things also that you should know. Like unlike some other algorithms, SVMs requires you to scale your data before you feed it to the model. As you can see in this example below, in the left plot, let's just consider that x1 is the height of something and x0 is actually the weight of something. Okay. So as you can see, the magnitude of height and weight are very different. So in this case, the street that is formed, since SVMs basically use the distance of the classes to form the street, if one class, if the magnitude of one feature is much different than the magnitude of the other one, it will like completely skew the street. So in this case, the street is almost horizontal. So it just classifies things on the basis of like whether something is over 62 centimeters or something is less than 52 centimeters. Now this is not actually really good because it doesn't utilize the x0 feature, in this case the weight at all. So what you do is you basically scale it so the magnitude of the feature is same, so it will like form a much better street. Another thing that you should know about SVMs are that these are slow models. Their time complexity ranges anywhere from square to cube. So if your data set is too large, like over 10,000 or 20,000 features, this could actually slow down. So make sure that the data that you want to fit your data that you want to fit is well suited for SVMs. And since the width of the margin will only depend on this and this, like the two support vector instances, the addition of any data which is basically like far behind, like somewhere over here, won't actually affect the width of the street at all. So one thing you could do is like you can really optimize your data sets in a way that they can be fitted to SVMs, and this could like really make your models train much faster. So like as you can see in this graph below, this is basically the interpretability versus accuracy chart. Like as you can see, the interpretability of SVMs is very high, and like the accuracy is also moderate. So it's basically a good balance between both interpretability and accuracy. You know, by interpretability, I mean like how you could visualize it as a street. You can't do stuff like that with neural networks easily. So this is basically the main terms of the SVMs. Like I told you, these two instances on the street are the support vectors. This is your main decision boundary, and this is a street width. This decision boundary is also known as a hyperplane. Now, all the data you are seeing currently is in 2D. That is why the hyperplane that has been formed is actually in 1D. So the dimension of the hyperplane is 1 less than the dimension of your data. So if, for example, this was 3D data, your hyperplane would be 2D. So now you saw how all the how class 1 is all on the left side of the street, while class 2 is on the right side of the street. So now can anybody tell me if we use the prior knowledge that we had, and if the one of the blue classes was on this side, what would happen then? How would the street be formed then? Can anybody answer me? So I guess since you're not answering, you don't know, so I'll just explain. So since it's this, it's not possible to create a street, because the street can't, go over that. It can't have margin violations in like, but that was because we were using hard margin classification. In hard margin classification, the classes need to be strictly on their side of the street. Okay. So one method to actually sort this out is soft margin classification. In soft margin classification, we basically allow some margin violations. In this case, you can see these things. These basically margin violations basically stand out, mean the instances that are either not on their side of the street or on the street actually. So using these margin violations, we can actually make the model a lot more accurate in real world use cases, because this improves the generalization of the model. So how is this generalization basically calculated? Is you basically allow a certain number of margin violations for that particular model. So example, the number of margin violations is calculated by using a hyperparameter known as C. This is basically the inverse of tolerance. So the lower the value of C is, the more margin violations will be allowed, and the better your model will generalize. Like, but you also need to make sure that C is not very large, because if like it's very if C is very small, because if it's very small, the street will allow lots and lots of margin violations, and this would actually result in underfitting. So you actually need to find some sort of Goldilocks zone for this. Now all of the above examples that I showed you was for linear data. So now let's discuss about some non-linear data. So as you can see, this is basically linear data. It's only one feature. So as you can see, it's not possible to make an SVM over here. The street won't be straight, and like you can't. So what you basically do is you just upscale this data, you convert it into 2 dimensions. So this could basically be, this is x1, and you maybe just square the data, and that way, since it's 2D data, it's not easy to classify. As you can see, you can either classify it like it being less than 6 or over 6, or you could maybe also classify it on the basis of the central line. So this is how it helps. As you can see, this is basically just the most simple form of increasing the amount of features. It's basically you just make the linear equation polynomial. But this also has its drawbacks. As you know, the more degrees you add, like more number of features it will create. So this could also go, increase the size of the data pretty much. And similar to the previous hyperparameter C, you also need to make sure that the degree of the equation is in some sort of Goldilocks zone. Because as you can see over here, for here the degree of the data is 3. Okay. So it's like fitting properly, it's like nicely generalized. But over here, since the degree is 10, it's fitting really closely. So this might end up overfitting. So now, like I said, since creating a lot of nonlinear features would actually increase the size of the data. So how can we actually do this? For this, SVMs actually have a nice little math trick known as a kernel trick. So what exactly does a kernel trick do? It basically assumes, it basically trains the model assuming that your data is actually in an infinitely high dimensional space. You can actually like specify what dimension you want to judge, but as you can see over here, since like this is 2D data, so creating an SVM over here would mean like going in this exact manner. But if you just convert it into a 3D feature space, you can find that you can easily separate it by using a 2D hyperplane. Like I told earlier, how the dimension of a hyperplane is 1 less than the dimension of the feature space. Okay, so and since this doesn't actually convert the vectors into high dimensional features, it will not exactly increase the size of the data. All right, so now the polynomial example that I showed you earlier, this one, this can also easily be converted into a kernel trick known as a polynomial kernel. So another thing that you should keep in mind when using these kernels is how much does the feature space of a higher dimension actually affect your data. All right, so there are hyperparameters for this. So basically limit the influence of higher dimensional data, which you might or might not want. Then there's a different type of kernel known as Gaussian kernel or Gaussian RBF kernel, radial basis function. So this kernel basically works on the basis of landmarks, and it tends to generalize features on the basis of these landmarks. Now let's see this image, the plot on the left. As you can see, we have chosen 2 landmarks, one on -2 and one on 1. So now you basically make Gaussian bell curves over here. Okay, so the closer and these curves range from 0 to 1. So the closer an instance is to this curve, the higher the value will be. For example, for just 1, this will be a straight line, this will be 1. For something like -3, this will be up to 0.75. So similarly, you can use these and create additional features, like as you can see here. And now this data is easily linearly separable, and then you can just use an SVM for this. This is the main function for the Gaussian kernel, and as you can see, this is like modulus of x minus y upon 2 upon sigma square. So what exactly is sigma? This sigma is basically like I told in the earlier polynomial kernel thing also, it determines how much these things would actually influence your model, the street formation actually. There's also another hyperparameter known as gamma, which basically controls the width of this curve. Okay, so now let's say the so it basically acts like a regularization parameter. Okay, so if for example this curve was narrower, okay, we influence the value of gamma, so this was narrower. In this case, the features that were more further out actually have less of a contribution on determining the street width. Okay, so now what I covered till now was actually the classification aspects of a support vector machine. Now let's get into the regression aspects known as support vector regressors. All right. So how do actually support vector regressors differ from support vector classifiers? Like the theory and math behind it is not that different, but the main intuition here is that instead of maximizing the width of the street to keep the two classes as far away as possible from one another, we maximize the width of the street to keep as many of the instances inside this this street. Now, just like I said, the hard margin and soft margin classifications also apply over here. The only difference is the margin violation in this case will be instances that are not inside the street. Okay, so like the width of the street can also be controlled by a hyperparameter known as eta. So like the higher the value of eta will be, the wider your street will be. So now you also need to make sure that this street is not too wide, because if it's too wide, then all your predictions will go haywire, because this decision boundary basically acts as a line of best fit, as it was also explained in the linear regression thing. And you basically, yeah, that's how it works. So now and similarly, even if the data is, let's say, skewed or polynomial, we can just use kernels, as I explained earlier, to just bend this street in a way that would include the maximum number of instances over here. So now let's get into the math behind the SVM. This is like really important. So now let's just assume that these are two vectors that point to the support vectors, okay, x and y. So x minus y here will basically x minus y will basically be the distance between the margin. Okay, so this x minus y in the direction of w, and here w is basically a vector that is perpendicular to this decision boundary of any arbitrary length. So this x minus y, a dot product of this x minus y with this vector w would actually give you the length of the street. Okay. So what you can basically do is, so the width basically amounts to this equation dot x minus y, and as you know, the general equation for support vectors is w dot x plus b equal to plus minus y. I'll cover this later. So now this is some basic vector algebra. You just take the magnitude of w and dot x plus b is to plus 1 and minus 1. So you then just substitute these two equations over in this one, and you get 2 upon mod w. So this is basically width. Okay, so now what would happen if instead of this plus minus 1, this was a plus minus 2 or plus minus n? Can anybody tell me? Okay, so what this plus and minus 1 basically decides is actually the slope of the plane. Okay, so now one thing that you need to do is plus minus 1 or n, anything, these two numbers should be same, because one of our objectives is to make sure that both the classes are equidistant from the decision boundary. Okay, so now what those plus minus 1 will do, they will basically try to influence the slope of the plane. Now let's assume that this gray plane, okay, this is the xy plane. Let's call this plane A, and then let's call all of these, any one of these planes B. So now this B plane actually has all the points in it. So now what that plus minus n will do, it will actually try to influence the slope of this plane. It won't have any effect on the optimizing function since n is actually independent of it. Okay, and as you can also see, so now I'll just show you how to actually optimize this function. Okay, so now let's assume there are like there's an arbitrary vector u and arbitrary vector w. Okay, now w is perpendicular to the decision boundary and as arbitrary length. So w dot u will actually be of projection of u on w. Okay, so now this w dot u, b is just a constant. So let's just assume w dot u, a is our class 1 and b is our class 2. So now this equation, if it's greater than or equal to 1, it will lie on, let's say, the right side of the street. And if this is less than or equal to 1, this will lie on the left side of the street. So now we basically have an easy way to separate these classes mathematically. So now we just multiply it by yi is actually our label. That means whether the class is +1 class or -1 class. So if this is 1, this equation will basically be the same. And even if it's -1, since by the law of inequalities, if we are changing the sign and we do this, so this will also become this way. Okay. So basically now to find actually this width, because this is the width that we need to minimize. Okay. We take two vectors VA and VB, and the difference with dot product W, as I explained earlier, even with X and Y, will actually be equal to the width. So here what do we do is multiply it with YA and YB and W dot VA plus B. So, and now when we just add these substitute these equations into this step 4, we'll actually get the same value as I showed before. Okay, so now what actually you do to get these equations is like I explained. Since the value of this will be +1 and -1, so this will basically become W dot VA equal to, the one side will be negative while one side will be positive. So everything will be cancelled out except this one. That's how you get this equation. So now what do? We basically want to minimize this. So one way to minimize is like we just directly minimize W, or the other thing is that we can also minimize W square. Now why do we minimize W square? That is because W square is basically differentiable. If you differentiate W, you will get 1. That will become constant. That will like ruin your equation entirely. So we basically just try to minimize W square because that's the thing. So but because minimizing W square will also indirectly minimize W. So we don't even try to actually minimize W square. We actually minimize W square by 2 because W square by 2 has a much better differential, that is just W. So now we use Lagrange multiplier method to actually do this. So this is the main equation that we get there. The alpha I here is basically one of the Lagrange multiplier. So then we just differentiate this with respect to L and with respect to W and B, and as Lagrange multiplier states, this entire thing is equal to 0. So you can just easily find out these values and substitute it in this big equation, the one in step 1. So doing that will actually give you this big equation, and when you minimize it, you'll get this. So now what does this thing stand for? This is our main function. This is our optimizing function. Like this is basically a maximization function, you could call it. So now what this thing stands for? This is basically this thing is basically the dot product between two different sample points. So this entire thing is basically the sum of the dot product between two different sample points. So this is how the entire maximization function works. Now, as you can see, this is like a pretty huge equation, and like since this is basically a quadratic problem, like it's basically a convex quadratic problem, so you can actually use quadratic programming to solve it as well. Like quadratic programming is out of scope for this session, so I won't go much in depth, but if you are interested in it, you can check it out. So that's it basically for the theory part. Now I'll just show you how to the code part a little. So wait a second, let me just increase the zoom. Yeah, so as you can see in this part, okay, I'm just here importing the libraries and all, and this is basically just an inbuilt data set that sklearn gives, which is the iris data set. Okay, so yeah, this is just some basic. We are using iris data set, which is basically the data set consisting of 3 different flowers. It consists of the length and width of the flowers, and we actually need to predict what kind of flower it is. So here we just separate out the length and width of the 2 flowers, setosa and varix color. As you can see, when you put this on a plot, you can easily see that this data is linearly separable. Okay, so now this data is SVM worthy. If we put it in an SVM, it will converge easily and we'll get a good model. So now we just we actually use a linear SVC class because we are just this data is linearly separable. One good thing about using the linear SVC class is that instead of a quadratic time complexity, it actually has a linear time complexity. So this, if your data is just linear, this thing will work much faster. And as you can see, this is basically the main confusion matrix of the data that we get. And here at the bottom I have plotted the SVM. So as you can see, there are certain margin violations as well. This is because the model generalizes well. So now this is, let me go into the implementation of kernels. Okay, so now this is just another data set known as make moves. This will basically create some non-linear data, which will look basically like this. All right, so the red part is class 1, while the green part is class 2. And as you can see, this data is not linearly separable at all. So basically use a normal SVC class. Now by default, this will just use a RBF radial basis function as a kernel, and it will fit to it. And as you can see below, this is basically how the entire mesh, the entire contour will look like. So like this is actually our decision boundary, like which is downscaled from any dimension to 2D. So yeah, that is basically the entirety of it. If anybody wants to ask a doubt or has a question in some part, just feel free to ask right now. Yeah, go ahead. You are muted, so I can't hear you.
Okay, sorry. Unscaled data को scale data वो क्या था?
What?
आपने डेटा को चेंज करने बोला था, unscaled data to scale data.
हाँ. So what about that?
उसको कुछ कोई कांस्टेंट से मल्टीप्लाई किए थे कि more samples.
You just make sure the magnitude is one thing you can do is just use standard scalar from SVM. It will make sure it has a unit mean and 0 variance, but or you could also use something like a min max scalar in this scenario, which will just mark the minimum value as -1 and maximum as 1, and feature scale everything in between. So that's one of the standardizing or normalizing methods that you can use. Basically, you need to make sure the magnitude is similar, so it doesn't actually affect it, because I guess if this is like as you can see over here, this is 60 into 40. So for some calculation, as you can see, if you just multiply these two, this number will be a lot higher than like 3 into 4. It will completely skew that. So basically, that's what you want to prevent. Like, is it clear?
Yes, sir.
Yeah. Does anybody else have any doubts? If no one has any doubt, then I'd like to call on Rahil Parikh, who is our lead mentor, to give some final words about this session.
Yeah, guys. So this was our first session, and we hope that you liked it and got to learn from it. So we'll be continuing to send some blogs and learnings on our Discord channel and our WhatsApp groups. So if you haven't been added, then you can text us. And there is one more thing. There's one feedback form that you guys need to fill. So I put that in the comment. You can go there and fill the feedback form. It will be very helpful for us because you can give your positive or negative feedback, whatever it is, and we'll look into it and next time try to improve.
Also, there's a doubt from Kaustav. So, Kaustav, what the aim of this session was for you to understand the theory and like form good basic knowledge about the algorithms that are taught to beginners, right? So that's why we used sklearn to demonstrate a more robust way of implementing these basic algorithms. Or you can definitely try on creating these algorithms from scratch. There are many different resources. Yeah, we can definitely share that on Discord as well. Please make sure to join. Does anybody have any doubts? Anything related to any algorithm you faced? Any problems?
We'll be sharing the recording on the Discord channel, so
yeah,
make sure you join there.
And we will also be having many such interactive sessions in the future. So please feel free to connect with us in our Discord server, and just make sure that you have fun overall.